Juan, can you let me know if you can hear me okay?
Yep, you're good.
Hello, everyone, and welcome to the 2022 Summit on Drone Geophysics. Today is day 2, and our topic for today is magnetics, multi-sensor, and exploration. We have had a really successful year in the last year, so we're happy to be back here on day 2. We had a fantastic day 1 as well with lots of good discussions. So I'd like to welcome and thank you all for attending. We have participants from all over the world today, and I'd like to thank you for joining in at different times. And I'd also have to give a special thanks to our sponsors. We have platinum sponsors today who will be doing a 10-minute demonstration in between the speakers. So that will be happening once a day. And I'd also like to introduce myself. My name is Keynote. I'm currently at BHP in their Toronto headquarters, serving as the principal geoscience data. And I'm spearheading some initiatives in the geophysics space within our global BHP team. My background spans airborne magnetics, gravity, electromagnetics, and radiometrics, primarily in the exploration space, but also in the software space and the geosciences. So I'm particularly thrilled for the topics that are being presented today because they're of interest to me. And I'm also joined today by my fellow co-chair, Juan Ortega, who will help me moderate the session. Before we get started and I turn things over to Juan, I'd just like to go ahead and thank our sponsors. We have our platinum sponsors, Mobile Geophysical Technologies and Sequent, our gold sponsor, Geometrics, our silver sponsor, Collier Geophysics, Etcon PRJ, Geonics, Medusa, and Southern Geoscience Consultants. We'd like to thank you for graciously supporting this program that continues to be successful through the years. And with that, I'll turn things over to you, Juan, to go ahead and introduce yourselves. Juan is also going to present the logistics and the house rules for today's session. Over to you, Juan.
Thank you, Kanita, and welcome all to the summit. It's been great to be part of it for the past couple of years, and I'm thrilled to be part of the Magnetics and Multi-Sensor Exploration Day. As I'm currently working for Collier Geophysics, I've been working and expanding the drone-based magnetics methods in the consulting world here in the States and international. I'm going to talk briefly about the house rules for each presenter. Each presenter will have a 15-minute to present and 5 minutes of Q&A. I will be doing the introduction for each speakers. And if the presentation goes into the Q&A time, I will ring a chime to indicate that there is a 1 minute left of the 20-minute total presentation allotment time. The presenter should begin to wrap up the presentation at that time. Whatever time is left for the presenter will be used for Q&A. And if there's no time remaining, any questions can be asked as part of the group discussion at the end of the day. During the presentation today, everyone will be muted, so please type any questions you have in the Q&A box. And then Kanita will be monitoring that, and she will be moderating the Q&A session. With that, I would like to introduce our keynote speaker. His name Robert Jackische, and his title is Drone-Based Multi-Sensor Data Integration in the Mineral Exploration, Mining Legacy, and Environmental Monitoring. So Robert, take it away.
Hello, can you see that? Can you hear me?
Yes.
Yes.
Excellent. Thank you. Okay, thank you for inviting me, and thanks for Callum to getting in touch with me, and I'm really happy to present basically what was 4 years of my PhD thesis, and the title of this talk is Drone-Based Multi-Sensor Data Integration in Mineral Exploration, Mining Legacy, and Environmental Monitoring, and I was part of a program which was called Multiscale, a project financed by the EIT, together with the Geological Survey of Greenland and Denmark, of Finland, and together with the company Radai from Finland and DMT from Germany. Okay, so why use multi-sensor drones? So when I started in around 2017, there were already a range of sensors available on the market. There was a little bit of magnetics, hyperspectral was coming, and multispectral and photogrammetry was already quite established. But those systems were not really integrated and used in mineral exploration. So there was a lack of integration of image spectroscopy and magnetics. And although they combine, or they show an ideal combination in geology, because you get surface material information and also information on the subsurface structure and magnetic realms in that sense. So in the course of my PhD, I also did a literature review, and I want to briefly show the results here. So I found, using different keywords in Scopus in the geoscientific UAV realm, around 300 papers, which you can see here. And it really started to kick off for UAV in geoscience around 2014-16, and separated from that for US magnetics is around 2016 to 17. But my survey ends at 2020, so of course there's much more now on the market. And when I mapped this using a software in a literature bibliographic network, you can see 4 distinct clusters basically. So you have in green and in red the UAV geomorphology, remote sensing realm. This all started 2010, 12, structure for motion and so on. And what you have in yellow, this is the hyperspectral realm. And in blue, this is the geophysical magnetic realm. And what you already see here, that those 2 realms, they do not connect and they do not talk to each other. They don't cite each other. So again, this shows there's an opportunity there to conduct research and to integrate those different methods. And why do not talk to each other? There was a lack of method transferability, maybe successful case studying, and missing technical guidance and workflows in that matter. And then talking about technology, I want to briefly introduce the drones that I worked with. So you can see here the multicopters used in my studies. So this is a hexacopter, an older model, mainly used for the hyperspectral acquisition. Then we have here the TOLEC. This is our working force, using the hyperspectral camera in this example, and DJI Mavic as reconnaissance drone, and also the fixed wings. So the big one in the middle, this is from the company Radai, and it's a smart solution. I never flew those actually. And here you can see the magnetometer in the end, in the tail, and in the top here, the engine. So there's already some distance to reduce noise. And then you see here the EB, this is the fixed wing, which we use for multispectral acquisitions and for photogrammetry. And also you can see our base station setup. Usually it looks like that. So you have your computers in the field, you have your drone and your reference panel to calibrate your spectral raw signal from radiance to reflectance in later processing steps. So now showing the sensors, which we used, and I was part of the integration and testing of those. So on the left, you can see here the hyperspectral camera integrated to the Tolicopter. This is a really nice device. It's a snapshot camera, and it stacks the bands when it flies. What that means, I will show in a later example. And it is variable in its spectral bands. You can change from around 10 to 380 bands, but we found that using 50 bands is the perfect amount to capture geologic meaningful information in the visible to near infrared, which you see here from 5 to 900 nanometers. So this is our range. And the flight time is around 15 minutes in good conditions. And the same you can see here. So the integration of the flux gate magnetometer from the company Sensis in Germany with a 200 Hertz sampling rate. What you already see is quite a small distance to the sensors, and I will address that a little bit. But it worked in our case studies so far. And for the fixed wing, we have the Parrot Sequoia, a multispectral sensor with 4 distinct bands here, very lightweight, and the EB Soda, which is a 20 megapixel camera and is used only for structure for motion and for high resolution auto mosaics. Then this sensor, this is the flux gate from Radai. This is an integrated solution, and it's already subsampled past to 10 Hertz. And the whole system as it comes is around 45 minutes flight time. And then I want to show this device here. So this is the spectral devices cam, and this was a prototype developed but not finished because unfortunately COVID came, so we had to stop the collaboration going to Finland. And the idea was to have a combined system in one drone, in one fixed wing drone, so having multispectral with 8 or 16 channels in the visible and near infrared combined with a magnetic system. And just a note on the side, so as I mentioned here, you see a small distance, so higher noise to the engines, and modern or advanced methods are, of course, for example, here the Teramis system by our colleagues, which increase the distance from the magnetometer to the engines. At the heart of my PhD is, so to say, using available and developing techniques to to go, so to say, from a 2D interpretation to a 3D outcrop model. And I don't focus now on all those gray boxes here, which show the different processing steps and so on. But of course, we can talk about that, or I can just send you the publications. But the real core is actually the fusion and integration of different methods to go to some geologic meaningful interpretations in those publications. So I don't want to introduce any magnetic methods here. I think this is quite common in this community, but just a brief introduction of hyperspectral mapping on a pixel basis. So what you see here in black, this is an ideal ground spectrum from 400 to 1000 nanometers. So in the visible to the near infrared. And what you would have for this example, this is a goethite, this is an iron oxide, are distinct features here. For example, you have an edge, you have the local maximum and a band minimum, and you can use those features to identify different iron mineralogies. And if you have a hyperspectral signal in an ideal case like that with 50 bands, you can really distinguish, for example, a jarosite based on its peak from a goethite. And if you reduce then your sample quality, of course, you have 4 bands in this example here, and makes it much harder to identify any material. And just for visualization, so what does it mean in terms of data storage? Now, when you go from RGB to multispectral to hyperspectral, you get a really huge load of data here. So the data cube shown, and you go from megabytes to gigabytes now, which needs to be addressed. And also needs to be addressed is the geometric, radiometric, and topographic corrections, which the colleagues worked on and still work on. This is actually key to create quality spectral data. But as I mentioned, with this camera, which I used, I only have a snapshot frames, which are stacked on top of each other. So I do not deal with those problems, for example, when you have a flying line scanner, where you have much more variation and issues you have to deal with. So going on now to the first case study. So this is Otanmäki in northern Finland. And this is a relatively small outcrop here. This is a gabbroic intrusion hosting large magnetite ilmenite lenses. And for us, this was a perfect playground to test our first setups with the fluxgate magnetometer and with the hyperspectral cameras in an exploration setting, so to say. Now, of course, you can see the surface was stripped from the boreal forest here. And then what we did is a ground survey as reference, magnetic ground survey, and a copter flight here. So this is 2 flights fused together. And what we get is this magnetic map, so the ground reference here, and then compared to the copter results, and we were quite happy with what we got because we really see similar or the same anomalies in this feature. And on top of that, we flew the hyperspectral, in the center of this area. And you can see here those different images stitched together. So those are my hyperspectral scans. And then after processing and interpretation, what I used then is the spectral angle mapper with ground targets to identify 2 different iron species here. So the iron oxide, which is linked then to the magnetite more or less, and also products from this oxidation, for example, sulfides, in a small amount, because now we have a lot of lichen, we have still patchy vegetation here. But anyway, using this data and fusing it together, we could create a relatively simple ore probability map as an example of data integration. So the second example was a bit more complicated. So this is in southern Finland in Silinjärvi. This is an apatite mine. There's a larger area with those exploration trenches, outcrops. And what we have here is a high surface noise. So there's a lot of moisture and soil. And we have actually a lack of spectral features in our camera range, so in the visible and near infrared. But we still want to distinguish different rock classes. So what we did is we flew with a fixed wing to get an RGB based on that and structure of motion elevation model and a multispectral scan, of course. And in those exploration trenches where you can see the surface here or here, the hyperspectral scans stitched together. Quite a lot of work to fly those and then to process it to some good quality data. And now, as I mentioned, we have no spectral features, but I still want to know my surface classes based on some training samples from the area. So what I did then is a multi-stage approach here, fused this data together using a machine learning algorithm, which is the OTVCA, which is using orthogonal total variation, combined with a spatial neighborhood of pixels. So it works quite well with those large redundancy spectral data sets, combining with the elevation and the multispectral. And then on top of that, so reducing the dimensionality of this was a support vector machine here with some training samples, and SVM is quite good with sparse sampling points to identify my classes. So my main features here were dolerite, carbonatite, glimmerite, feldspar, and phenite, and my community is basically the carbonatite. But this is just the surface. Now integrating this with the magnetics, as I mentioned here, we have a magnetic flight and we see a distinct anomaly. And what I use then is a straightforward forward modeling to create blocks in depth where I have some susceptibility. I have an idea from literature how deep they should go, and I could directly or nicely constrain them in 2D based on my hyperspectral fusion model. And then using the photogrammetric point cloud and the compass tool created by the colleague Thiele here, Samuel Thiele, to extract also structural information and then to sort of paint geologic outcrops, of course, also 2D maps in depth based on real data, not just on, let's say, a geologic interpretation. And this was confirmed by the mining company. And one benefit of this study was, as a sub-publication or as a main publication from a colleague René Boysen, that we could identify rare earth element features in the carbonatite, because there the apatite has a neodymium and small traces of dysprosium, so all in very small abundance, but still rare earths have those distinct absorption features in the visible, which is the range of our camera. So at 580, 750, and 800 nanometers, we have those small features here. And we could identify that in our hyperspectral signal. And another benefit here of, again, mentioning multi-sensor data is the combination fusion of RGB and hyperspectral in an unsupervised sparse clustering, which was the work of another colleague. So my third case study here, now we go actually to a real, more or less exploration scenario. So this is in West Greenland. This is Disco Island. The area is Cooley-Set. And here we basically left the copters in the box and we used the fixed wings. And what we used is magnetics and multispectral photogrammetry in this basalt, flat basalt province to investigate for nickel, cobalt, and copper here. But the problem is that those rocks, our target formation here, the target body, which is barely seen in the topography, was formed during a time of magnetic field reversal. So it has a distinct remanence, and it's really hard to interpret that with normal methods. So what we use is the Voxy magnetic vector inversion. But just I want to show also the advantage again of using drones. So what you see in the left, this is the legacy airborne data. So we have 4 flight lines, and it's quite complicated in this topography to fly safely. But again, the guys detected something, and this was, I think at this point, there was 1 drill hole, which was successful. And in comparison, we see here the ground coverage. It's really tedious to do this in this kind of scenario. And in comparison to that, also the drone here. This is 4 hours netto flight time. And you can see our anomalies here linked to the remanence of this basalt. Now going on, combining this in the Voxy using morphology and really creating a constraint model then, we go on. I have to wrap up a little bit already. And what we get is distinct bodies here, so realms of susceptibility in the subsurface. And this is then used actually right now for continuing exploration in the area. And we were really happy with this result to get the structure in depth. And Cobalt Metals is actually the company which is doing investigation now in this area. Now, as mentioned, I also want to show what happens after mining, post-mining and environmental monitoring, so mining legacy. So this is an example. This was actually my master's thesis starting at Helmholtz. And what we did here is we went to the Czech Republic. There you have those mining legacy from lignite mining. And what we mapped here in hyperspectral scenes is 2 distinct minerals, is jarosite and goethite, which are indicative for distinct pH regimes. And in this example, jarosite is a proxy for lower pH values in this area where the water is drainage from a tailing in the north. And based on that, again, showing here the spectral features of those minerals, we can identify it in the visible and near infrared. Here, jarosite, goethite, schwertmannite, and hematite. A colleague then extended this in Spain. This is the Rio Tinto area, what you can see here. And there, of course, mining is done since 3,000 years. So people are used to that. And what we have is a low pH water mixing in this confluence area with a normal, let's say, a river stream. And he used then hyperspectral information to do a regression together with ground samples, water samples, to mix distinct, to show distinct pH values here, which work quite well. And the last example, so this is now, we leave mineral exploration and legacy mining and go now to forestry, because I wanted to show what I'm working on right now. So I was invited by the Alfred Wegener Institute to go to East Siberia. This is the Republic of Yakutia. And there you have those massive wildfires in the boreal forest, which you can see here, those smoke plumes. But of course, you all know that from northern Canada, from America, the US, and those white points, those are all our sampling spots where I flew the multispectral and the LiDAR. And this is just a result here. So this is a beautiful point cloud from the boreal forest. Those are actually small, large trees, which take around 150 to 200 years to grow. And you also have those permafrost features here, those polygonal ice wedges. And the whole system now is changing. I don't know what will happen in the future with this data, but right now we work on that. The main idea was actually to have a continuous sampling campaign. But yeah, situation is a bit complicated. We all know that. And this is just now in 2D looking at this. So what you see on the top left, this is one of those vegetation transects. So in green, we have the boreal forest, and in black, this is the charred ground, the burnt forest, so to say. And again, the advantage now of using UAVs, you can fly this in half an hour compared to the ground truth, which you need. But those plots, they take several hours to acquire all the ground truth you need for later estimation of biomass and of real biological analysis. The other plots show the thermal signal from the multispectral camera from the Altum. And you can see here the NDVI. So what is interesting already now with even not much analysis is that you have kind of a buffer where the fire came, it burned the ground fire, but it stopped at some point here. And this is maybe related to permafrost features or topography. And also you get nicely the vegetation height from the LiDAR here now. So wrapping up, so coming to my conclusions, yeah, we showed that US magnetics are feasible and quite accurate. US hyperspectral can directly detect surficial iron and rare earth elements, but multispectral can indicate iron alteration. And we have applicable workflows with the tools, but the limitation of my studies were that the hyperspectral data was done on small study areas. No? And your cameras, your sensors limit the mineralogical suit. And of course, illumination, geometry, and surface cover will always be a problem with surface scanning techniques in the visible and in the near infrared. And of course, data processing and corrections are key to get quality data. And coming from Outlook, so as I mentioned, those are relatively small study areas, but of course they can serve also as calibration products for upcoming hyperspectral satellite missions, for example, Nmap, Prisma, and SHIME. You can apply those methods in other fields of research, and there's potential to integrate smaller sensors. And one driver there are, for example, the automotive industry, which use LiDAR, which use sphere cameras to detect, for example, upcoming cars when there are cloudy conditions or fog on the streets. And those things can be applied for drones as well. Thank you for listening, for being here. And I want to point out that there's a free ebook, UAVs for Environmental Sciences, which you can download here. And we have 2 chapters in this. Thank you so much.
Thank you, Robert, for presenting some very compelling case studies. You eloquently covered really just a whole range of the mining life cycle there, from exploration all the way to post-mining and environmental monitoring. I especially enjoyed that last, one of the last examples in exploration with the nickel copper site in Greenland. The coverage is definitely quite comprehensive with the drone as you presented it. I'd like to open up the floor for any questions. We have just this minute here for questions, so please send them through. Okay, I have one already. And this one is from Callum. He also commends you. Excellent talk. Thank you. What do you think are some of the most promising multi-sensor combinations Some examples I can think of are hyperspectral mag, gamma ray mag, and EM mag. I'll let you answer that, Robert.
Thank you. Thank you, Callum. Great question. That's a good one. Actually, now my feeling is that hyperspectral is sometimes too much. So I would say maybe good multispectral and mag is even a better combination, or using other spectral ranges like the shortwave infrared could be really advantageous. I haven't worked with gamma and mag, to be honest. Probably they integrate well. The same goes for EM and mag. But coming back to hyperspect, which I feel comfortable to talk about, is really sometimes it is too much. No? So having distinct spectral bands on a smaller system can increase really the lines you produce or the area you can cover. No? How deep did the magnetics go in case study 3? I think it's about 100 meters, if you can say. So the one drill hole we have has a depth of 100 meters. Yeah.
Okay, and then for the REE identification, what is the lower bound limit of concentration before we lose detection?
I have to say, I don't remember. So the concentrations were really, really low. And of course, this depends on your flight elevation. But at some point, if you fly too low, and of course you could walk, or you use a really high resolution sensor. But it's in the range of maybe 1%. I have to go back to the paper to be sure.
Sounds good. Unfortunately, I have to just cut it off and go over to the next speaker, but there's lots of questions coming through still. I'm going to save them for the discussion. So if you didn't get your question answered, this is not the last time. So Robert, you'll be sticking around for the discussion. We'll be happy to maybe take some of those questions over through to there. Thank you so much, Robert. And with that, I'll turn it over again to Juan to introduce our next speaker.
Yeah, thank you. Next speaker, it's discussion is going to be on dual radiometric and magnetic drone system. And the speaker, it's Alex Coutu with the affiliation on ROSOR. So take it away, Alex.
So hello, everyone. It's a pleasure to be in front of you today. Hopefully I can actually make it through and I won't be choppy here and there. As I was saying before I got cut off, was today's approach is going to take more of a platform focus rather than Robert's data approach. We're really looking to accommodate the available sensors and maximize upon what is possible with the drone itself, what it can lift, how far it can fly. So I'm here today to present the dual radiometric and magnetic system to see more and see further. A little background on ROSOR. Essentially, we specialize in the drone engineering side of things and look to cater to the geophysical market to really.
I think we lost your audio there again, Alex.
Area. Their flight times are much slower or shorter. They're very slow, which leads to an unscalable system, right? Going into more BV loss operations, we have that ability to scale, right? Making the whole survey more economical, kind of looking more towards the helicopter survey. Also, you typically see, unlike the last presentation, one drone, one sensor, leading to, of course, less data and less insight. So advantages that can be provided on future systems. Of course, the key pieces that we really focus on are the payload capacity as well as the flight times. So with greater payload comes, of course, greater sensors, right? EM, it has its own weight constraints. Other sensors outside of only magnetic certainly have more demand. And of course, with that greater weight, right, it's essential to be able to fly those longer flight times in order to reach that scalability point. So that's what we really focus on here. Now, this single experiment was made to really present and demonstrate that high resolution difference over those traditional systems with, of course, the integrated platform. So what we do here, what we took on in the experiment was to compare the regional versus the local, looking at, of course, multiple data types from the traditional aircraft, and then see how our system, right, lines up. So in this large regional survey, just on the border between Ontario and Quebec, west of Renfrew here, we took on a small survey area, and within that small area, even smaller components. So the challenges to the survey, of course, tackling those real focal points was that payload capacity, overcoming that payload weight demand, that short flight time, and of course, the drone's endurance. Comes the legal hurdles. Over here in Canada, we have our special flight operation certificates that are needed. So our goal that we really went for was a 90-minute flight time. We greatly succeeded that, along with our 50-kilometer endurance. So just breaking down our system here, we have the Roser Recon Heavy. This is, I really want to focus on what we call in Canada the remotely piloted aircraft system, with emphasis on system. What we do is we don't reinvent the wheel. We take all these different subsystems that best suit the application and put it all together in a great system that will best fit. So this system in particular, we've modified it from readily available subsystems. It's a hybrid gas electric aerial platform, of course, to support the different sensors that are needed. So for this experiment, we had the Geometrics Mag Aero, as well as the Radiation Solutions RS530. Now, we were able to acquire our SFOC for this operation as necessary. This aircraft in particular, the Recon Heavy, has a maximum takeoff weight of 49 kilograms, of course, exceeding that 25 kilogram ceiling. So using this, we acquired the SFOC to be able to fly that for this specific operation. And of course, the pilots that were flying it have their advanced RPAS operation certificates. Now, all of our crew members come minimally equipped with that level of certification. So now just a quick glance of the system in action. This is it flying near surface. On the hull itself, we have the gamma ray spectrometer. It's hard to see it there. And then the mag arrow just suspended about 2 meters above the ground, right? So level of QA/QC was applied, and no, I don't have my numbers right in front of me, but essentially the mag arrow was able to output sensitivity within 0.04 nanotesla, if memory serves. The diurnal correction and the base mag 0.06. For some reason, my script isn't showing up here. But anyways, it was QA/QC was applied, and we got very clean lines that were quite noise-free for the localized survey. For the radiometric, we're able to really see a lot of repeatability across the different lines. No outliers, showing good, consistent data. Now, taking a step back towards the radiometric, for a lot of you, this is going to be quite basic, but essentially the spatial resolution that you see from the RS530, 80% of the concentration or the area will be acquired from the bottom of the sensor itself. That's where this line comes in. So from an infinite source, we're really seeing the radius of our acquired area to be according to the graph, acquired by the manufacturer, approximately twice the height. So that's for uranium. Of course, for potassium and thorium, they have different energy levels, of which thorium is highest. We take a look here. Since we were flying very low, we look at the 5 meter height and our radius of, if we go up here, approximately 10 meters. Now, if we compare the traditional aircraft and the way it was flown, it was at approximately 100 meters versus ours. The spatial resolution increase, of course, as you'll see, were levels above what you'd see from those regional surveys. So that's what we're focusing on here. After we accomplish the regional survey, the best use for these systems are to further hone in on those anomalies themselves so that we can more accurately focus our intrusive ground level geophysics and those drilling targets. So some practical resolution results that we received here. When we look at the map, the gray line here that you see was actually the regional level survey flown by the Navajo PA-31. That was with a Geometric's G822 magnetometer, as well as the RSX 6 gamma ray spectrometer. So what you pick up from that is this anomaly here. It's a relatively known quantity. And when we compare it to our results here with much thinner line spacing, in particular, these here were flown at about 14 meters line spacing, we're able to catch, of course, a much more defined anomaly. It greatly differs from the regional that you would see. Of course, this is as we would expect it. It's a whole other thing to really showcase it and demonstrate. So the differences are quite vast. This one's my personal favorite, right? From here, right, we have in between the lines themselves of the traditional survey, right, there's that limited insight. It's inferred, right, after these filters are applied, you have a big blur. But what we have the ability to do with the RS530 is to focus on these different little specks that are within that blur. Now, future upscaling the system, this is in the works and en route. We are actually looking at supporting larger crystal sizes. And if we compare more specifically a 4-liter crystal pack to a 16-liter, if we're flying much lower in general, we can see a very similar performance gain. But with the larger drone that's flying at, say, between 20 to 40 meters above ground, you're really getting that extra spatial resolution, whereas, say, a helicopter flying higher between 60 to 80 meters, right, would really be hindered. So the system would, of course, support your longer flight times than what you have on your all-electric, readily available systems, and of course, longer endurance. As for the magnetic results, we have a similar result where really those areas, as we would expect them to, are much greater localized much more effectively, right? The anomalies, again, are much better defined. Another example here from another survey area. And then this one. So much like the radiometrics, you're seeing sections within the greater blurred anomaly. And now for good measure here, just a quick illustration, is when both systems are flown independently and combined. So we were able to fly the same flight route, having the tethered system, the mag underneath the drone, while the radiometrics was flown on, again, the fuselage, whereas here it was only the radiometric sensor that was flown about 2 meters height, whereas this closer to 15. You actually do get a similar result. Just at the end of the day, the reason for that is just to get closer to prove that, of course, magnetic and radiometric would work in a combined form. Now, of course, as in traditional surveys, that is known. It's just the proof is in the proof. So we really just do due diligence. Now, going further, adding more systems to this aircraft, this platform, of course, having a larger headroom for payload, there's a lot more possibilities. LiDAR and VLF being the most simple to begin with going forward. These are optional add-ons. Now, a little bit more detail into the payload capacity available with this hybrid gas electric drone is it can support that 90-minute with flight time with 10 kilograms payload. Having that 10 kilogram payload weight capacity, we can of course fit in these VLFEM sensors in addition to the radiometric, very lightweight sensor and that Geometrics mag arrow. Those come in at approximately 4.5 kilograms, which would very easily be able to accommodate VLFEM. Different configurations, of course, are possible depending on the application. Now, that's really it for the presentation today. To get in touch, please feel free to email. That's the best, and consult with our team today. Thank you very much.
Thank you, Alex. And yeah, nice to see that you're making some progress with the mag radiometric system there. Are the LiDAR and VLF options currently available commercially, or is that in an R&D phase?
So the LiDAR is more so in the R&D phase, but the other is available, correct.
Thank you. I think I can do one question here. How low does the system need to be flying to get usable data, and what kind of depths of detection are you finding? And that's from Maximilian Orman-Colmer.
It's a great question. The limiting factor is actually the radiometric sensor. Because it's a much smaller crystal size, about 3 by 3 inch, you wouldn't want to fly that particular sensor over, say, 25 meters. But of course, the aeromagnetics are totally fine. VLFEM as well as magnetics, there's really no limit. But of course, hanging on to the benefits of these systems, we like to fly lower, below 50 meters, right, skimming the treetops about, in an ideal case, 20 meters above ground.
Well, thank you, Alex. And we're at time here, so thanks again. And I'll look forward to speaking with you more during discussions. I'll hand it again over to Juan to introduce our next speaker.
Yeah, thank you. Awesome talk, Alex. The next speaker, it's Filippo Accomando, and his presentation title is a drone-borne magnetic survey to map an igneous dike and intruded in carbonates. So Filippo, take it away.
So good morning to everyone. I'm Filippo Accomando. I'm a PhD student from the Department of Earth Environment and Resources Science of Naples. And in this study, I will illustrate the acquisition techniques and the related data processing used during a drone-borne magnetometry survey for the mapping of an igneous dike intruded in Mesozoic carbonates. You know that in the past decade, the introduction of the wavy platforms, commonly known as drone, and the development of miniaturized lightweight magnetic sensors opened new data acquisition possibilities. In fact, the drone-borne magnetometry allows collecting magnetic dataset characterized by uniform aerial coverage and a good resolution, representing an intermediate solution between the classical ground and the high altitude airborne prospection. Drone-borne magnetometry allows reducing also cost, time, and risk with respect to the other acquisition technique, and allow performing high resolution survey over places of difficult access. For example, in the case in presence of dense vegetation, cultivated area, swamps, glaciers, lakes, for a short area, or along steep mountain slope, ground survey cannot be feasible, while classical area magnetism may not provide the requested resolution. We know also that one of the main problems related to the drone-borne magnetic survey is the magnetic and electromagnetic interference due to the platform and its engines that could compromise the quality of the data. So there are different strategies to mitigate this noise that operate both in real time and post-processing, and one of the simplest and most effective strategies is to suspend the magnetometer at a certain distance from the drone. However, this choice could compromise the stability of the flight, for example, in case of windy weather, and can create a wanted periodic variation in the data generated by the oscillation of the magnetometer sensor. However, in a recent work, we show that in the case of surveys of intense magnetic anomalies, as those expected in the studied case of an igneous dike hosted in carbonates, a practical solution for carrying the magnetometer may be to rigidly attach it to the drones landing there. Therefore, in this study, we conducted a drone-borne magnetic survey on the southern western slope of Monte Cesima Ridge, some few kilometers far from the Rock volcano, and here, within the active quarry of Taverna San Felice, we performed a magnetic mapping of an igneous dike intruded in Mesozoic carbonates. This image clearly show along the quarry wall the southwestern northeast trend of the dike from the bottom to the top of the quarry, while the details in figure C show very well the high transverse thickness of the dike and the metamorphic areola along the contact between the dike and the host rock. Then, associated with this large magmatic dike in the upper part of the quarry, there is an over 50 meters thick stromboli pyroclastic succession associated with a system of monogenetic vent, probably fed by the dike itself. This video, the aerial photo and this detail help to better understand the complexity of the investigated area, which include both of the active quarry unstable and not easily accessible for ground survey, and the steep mountain slope with the bush vegetation. The elevation of the excavation front varies between 200 and 400 meters, as shown in the topography model, with the complex terrain geometry due in some part of the quarry to 5-7 meters high steps. And considering the rough terrain, the use of an UAV for the magnetic investigation was the only strategy for the investigation of the area. Magnetic data were acquired by a geometric microfabricated atomic magnetometer in the development kit version, which is a laser pumped atomic magnetometer with the 2 alkali vapor chest sensor, and thanks to the high sampling rate of 1000 Hz, it allowed obtaining an aliased measurements of 50 Hz field relative to power lines, and also the correct identification of the high frequency magnetic noise due to the rotary aircraft used. This specification, in addition to its small weight of about 1 kilogram and the high sensitivity, make this magnetometer ideal for drone survey. We house the magnetometer in a light aerodynamic and non-magnetic custom board made of polystyrene with a thin and rigid base, and the total payload weight was about 2 kilograms. About the flight path, to cover all the studied area, 9 individual surveys were flown at an elevation of 20 meters above ground level, and the flight path show what I said before, I mean, a high altitude range variation in the flight along each profile acquired, from a minimum of 220 meters to a maximum of 410 meters. In total, 81 north-south parallel survey lines of different length were flown with an approximate 10 meters horizontal line separation. And overall, each flight duration was approximately 15 minutes long, and in total, over 16 kilometers of data were collected. The pre-programmed flights were conducted at a speed of 2 meters per second, and considering the flight speed and the magnetometer operating at 1000 Hz, the spatial sampling step of magnetic data along the survey lines was about 2 millimeters. This low speed allow a good spectral separation between the signal and the noise, and this is very important in the case where the magnetometer is too close, is very close to the drone. In fact, to estimate in the time frequency scalogram the frequency band associated to the target signal, we can evaluate the ratio of the UAV speed and the anomaly horizontal extent, representing a half wavelength of the signal, multiplied by 2. So assuming an anomaly half wavelength of 15 meters, we see that a slow speed assure a good separation between the spectral representation of the anomaly and the noise, while on the contrary, a high speed corresponds to a signal frequency very near to the expected one due to the magnetometer oscillation when it is suspended at the standard distance of 3 meters. So the first step of the data analysis was the subtraction of the international geomagnetic reference field from the measurements obtained by the magnetometer during the survey, actually a constant value as the surveyed area has a limited extension. The unfiltered data in the blue line, figure A and B, show a high frequency and high amplitude noise with a maximum amplitude of about 25 nanotesla, which was present during all the flight duration. So a spectral analysis in the time domain through the continuous wavelength transform allow the study of the frequency content and the identification of the bands that can be associated with the signal and noise, as shown in the figure C. While in figure D, the figure D shows the sum of the scalogram at each frequency, and the evident peak around 50 Hz present in both figures can be interpreted by the presence of the magnetic and electromagnetic interference field generated by the UAV, and to a lesser extent also to the power electrical lines present in the area. Therefore, we use the low pass filter with the cutoff frequency of 1 Hz to remove the noise and preserving the frequency content of the signal. So from the filtered data, we obtained the total field map, which show a maximum amplitude variation of about 1,700 nanotesla, with detect two main anomalies with a different trend, shape, and amplitude. And the southern feature has a dominant northeast southwestern direction and appears clearly as the effect of the dike, which emerge following the same azimuth along the upper part of the quarry wall. In the northern part of the map, the broader anomaly located further east of the dike displays the greatest amplitude and is correlated to the exposed Strombolian pyroclastic deposit. Thus, the most intense anomaly may be spatially coincident with monogenetic vent fed by the dike, while the area C indicates a group of anomalies are related to the volcanic products and due to tracks present in the area during the surveys. Okay, a subsurface model can provide important information for the geological interpretation. For example, to understand the propagation mechanism of the intrusion, its thickness, and to obtain useful information for the reconstruction of the stress field at the time of the intrusion, as well as for the studying the influence of pre-existing faults that could have influenced the direction. So first we perform 2D forward modeling along three different sections. The first one crosses the part of the dike that emerge along the quarry wall, and the 2D model, starting from the no geological information, that is the main thickness of 15 meters, and the depth of the body equal to 0, we estimate a magnetization of 8.8 ampere meters. The data in the blue circle are related to the tracks present during the survey, so they are not considered in the model. The second section crosses the northern part of the dike, and this is also the buried part of the body, which is not visible on the ground. Therefore, in this case, we use the dike thickness and the magnetization estimated before as constraint to calculate the depth of the top of the buried body, and the 2D model estimates the depth of about 7, 8 meters. The last section across the main part of the Strombolian pyroclastic succession associated to the dike, and also in this case using the thickness and the magnetization as constraint, we estimate at the point with the highest magnetic field value a maximum deposit thickness ranging between 15 and 20 meters. Finally, we perform a preliminary immersion of the data to obtain a 3D information on the geometry of the dike. We use the Lee algorithm to provide a smooth model of the source. Before the inversion, we use the upward continuation from the acquisition surface to a constant altitude of 410 meters. And this operation was carried out considering the complex topography characterized by high difference, as shown by this 3D model. The preliminary magnetization model obtained show a strongly magnetized surface body in correspondence with the area of pyroclastic emission, which in depth extend in the southwestern direction. So we can conclude that for this study, the use of an AFB for the magnetic investigation was the only strategy for the investigation of the area. The magnetometer attached to the drone's landing gear could represent the best survey strategy when with intense magnetic anomaly such as those observed in this study, and in all the cases when it's necessary to increase the flight security and stability. The use of a magnetometer operating at fast acquisition rates, a low and adequate sampling, and a successful filtering of the high frequency typically associated to the UAV electromagnetic noise, and the dike geometry information obtained through the forward modeling and the preliminary data inversion are consistent with the structural geological data collected on the field. So thank you for your attention, and I'm open to the questions.
Okay, perfect. Thank you. We are right on time here, so I'll welcome any questions. If you have any questions, please pop them into the chat. And thank you, Filippo, for an excellent presentation. I like that outline all the way from survey design all the way to processing and conclusion.
While you get those questions, Kanita, I have a question for Filippo. Filippo, why did you, just to recap, why did you had to attach the sensor to the landing gear? Why was that critical in this case?
During the talk, I show the very well the area. Also in the video, I show you the very difficult situation. So and the high altitude variation. Also the weather condition was not optimal. So for us, we choose this configuration for safe to have. We choose this type of configuration for to have a configuration more safety, and also to not have a lot of oscillation of the system, because this type of oscillation can give some problems to us in the data processing. So for us, that was the best solution.
Well, I'm glad it met your standards, and you were able to, using that configuration, you were able to see your target. Good.
Great. I'll take one more question and then we'll go off into break. I think we can probably answer this quickly. What was the cost for developing and manufacturing that sensor?
Because I don't understand the question, because before I read the question about the cost.
Yeah, it's about the cost of developing and manufacturing that sensor.
Yeah, the cost is very cheap if the question is related to the bird. If it's related to the sensor, the cost is on the internet. So it's an easy task.
All right. We have other questions here, but I'm saving them all. So I think we can head off into break. We can take 20 minutes here and come back at 25 past your hour. It's 11:07 for me, so I'll come back at 11:25. So 25 past the hour, and we'll see you all back then.
Welcome back, everyone. We're going to continue on with today's day 2, magnetics, multi-sensor, and exploration. For those of you guys that are joining in, the next presentation is with Johannes Stoll. He's going to be talking on the drones in geophysical exploration. A new era of automation is coming. That's his title. So Johannes, the floor is yours.
Thank you very much. I'm also very grateful to be invited as a speaker to present some ideas about the geophysical exploration using drones. And it's, I think drones are made to automate the geophysical work, field work. I have 4 points. First, driving forces and key developments. Second, role of drones in geophysical exploration and future trends. And I would like to present you some novel geophysical instruments. And then I have 3 slides about future trends in geophysical exploration. I think one of the driving forces are the costs of mining. Costs in mining become extremely high when it comes to production. So for the investors, it's very important to achieve as much as information as they can get from many disciplines. One is geophysics, and in order to define the location of drillings, it's very important to use geophysics, because geophysics is the more or less sole geoscientific methodology which can look deep. So drones may help to reduce the costs for an investor to achieve information on a very, very dense measuring grid. And the investor has to make, at some point in the development of a mine, he has to make a decision where to drill. So I think drones can help to facilitate this decision. Second, over the time, in the last several decades, it became clear that the exploration is done by under deeper cover. So geophysicists are forced to invent methodologies that can look deeper than a few hundred meters with high resolution. So this is a second driving force. A third driving force is, as we already know, the demand for copper to do the transform into a CO2-free, net-free society requires a lot of copper. And it became clear that in the next 25 years, the world is going to mine more copper than what has been mined in all history before. And the exploration that is done currently is not enough for this demand. Another driving force is that, especially in industrialized countries, the need for high-tech metals has grown over the last decade. And it can be shown that in order to do the transformation into a net-free, CO2 net-free society, we need big amounts of so-called rare earth elements. And it's very important to understand for geophysicists that they have to do more research, especially using drones, to get more information about possible deposits or prospects which contain rare earth elements. Drones are a very complex system. They rely on numerous key developments which show a long timeline of development in the past. Drones benefit very much on the development of low-cost mobile PCs, also on smartphones, and also on the many GPS satellites, which can be used not only for positioning, but also for synchronization, time synchronization. And in the last decade, the industry showed that more commercial drones have been built, manufactured, and sold than military drones. In the future, UAV formation flying, also in geophysics, may become more important. We also saw a very well development of mini drones in the past. When I started my business 12 years ago, almost only large or heavy drones were available. There were some mini UAVs on the market, but the quality and their reliability were too poor to do commercial projects. Third, geophysics also have shown a lot of key developments in the past, especially the sensor array techniques, then the developments in airborne electromagnetics, heli-TEM, and the development of high definition instruments, magnetics and EM instruments. These developments now can be used on drones. 10 years ago, all these systems were very, very heavy and couldn't be lifted by drones, not at all by mini drones. But in the last 10 years or 5 years, many manufacturers have released new sensor systems which are light enough to be lifted by drones. And last but not least, the numeric modeling and inversion of magnetic measurements, and also of 3D and 2D measurement grids of electromagnetic measurements became only possible by the development of 3D numeric modeling and inversion codes. Without these developments, it wouldn't be possible to use drones and perform electromagnetic measurements over large grids. And I see a fourth development which might become very important in the near future, artificial intelligence and virtual reality. Something about, I can't read the headline, it's, yeah. Why are drones important? Drones are a link between ground measurements and traditional or standard airborne EM or airborne geophysical measurements. Here I show a typical survey of CSAMT on ground, which can achieve 5 kilometers per day, and it involves 5 to 6 people to achieve 5 kilometers per day. Magnetics on ground usually can achieve 10 kilometers per day, sometimes maybe 15. But a drone-borne mag survey can achieve 70 to 80 kilometers per day. And a semi-airborne electromagnetic survey using drone can achieve also 70 to 80 kilometers per day, which corresponds to an area of 4 square kilometers. Using fixed-wing UAVs, in the future, it will be possible to achieve 500 kilometers per day, which corresponds to 50 square kilometers. Here you see an example of a survey I have done in Turkey some time ago on a gold prospect, where we achieved 16 square kilometers, 4x4 square kilometers in 9 days plus 1 day to do reflights. And in the graph below, you see what we have achieved per day, the production rate per day. It's important to note that all the time we flew more than, or we flew more kilometers than required, because from the base stations, the ground station, we have to fly the drone to the profile, to the line, first flight line, which is in some cases, depending on the topography and the accessibility of the area, can be 1 or more kilometers. So we fly always more lines than which are than on the grid, on the production grid. The flight altitude usually is 50 to 100 meters above ground. And in this case, the total distance was more than 650 kilometers. This is the result. We did airborne magnetic measurements on this 16 square kilometers. The area was very, very rough and densely vegetated, with high trees up to 40 meters. Another example are electromagnetic measurements. 2018, we have released a system which allows to do electromagnetic measurements on drones in combination with magnetic measurements. This year, we have also developed a navigation system which allows high precision measurements of the location of the X and Y, of the horizontal position, and also of the vertical position with an accuracy better than 50 millimeters, 5 centimeters. This comes in combination with post-processing of raw GPS data. And this high precision navigation system will help us to locate pipelines with a very, very high accuracy in the order of a few centimeters. The EM system comes with a 3-axis induction coil system, which has a bandwidth between 100 Hertz and 500 kilohertz. We measure 3 channels with a sample rate up to 524 kilohertz. And it's weight reduced down to 3.5 kilohertz. The sensor consisting of the 3 induction coils weighs only 2.1 kilogram. So in total, it's a little bit more, it's almost 6 kilogram, the total weight. It allows to do so-called very low frequency measurements. I will give you an example from a survey in North Norway, where we used 2 marine radio transmitter stations, one located at the east coast of the United States, the other one in Norway. Using 2 transmitter stations allow to perform so-called tensor measurements, because we have excitations of plane fields from 2 different directions. This is the scene, the survey area, very cold, minus 25 degrees, only accessible by snowmobiles. And the principle we had used is we use the frequencies from two radio transmitters, one located at the east coast of the United States, Cutler with center frequency of 24 kilohertz. The other one located in Norway with 16.4 kilohertz. It allows to estimate the tipper and plot it over the survey area. Here you see the results for the US-based transmitter station and the Norwegian transmitter station. And as a result, we are able to combine both measurements to a so-called peaker. It's a complex number with a real and imaginary part. And applying this methodology to our measurements, it gives us an excellent result of conductivity changes in the subsurface. So this methodology allows us, using these 2 radio transmitter stations, to plot conductivity changes and map geological tectonic structures in the subsurface. Another methodology that can be used is the semi-airborne EM methodology. It was inspired by Smith, Annan, and Gowan, who published a paper about semi-airborne measurements and a comparison with true airborne measurements and ground measurements in 2001. This methodology uses a horizontal electric dipole placed on ground and with a receiver attached to the drone flying along flight lines perpendicular to the direction of the horizontal electric dipole. We measure the current at the transmitter station and also the magnetic field on the receiver attached to the drone. And if the turn on, turn off is sharp enough, we produce a lot of harmonics that can be used to evaluate the conductivity changes in the ground. Here you see an example that was achieved in Hamburg in a groundwater exploration program, and it was modeled. The purpose was to get information about so-called paleo channels, which can be a very good source or very, very good deposit of fresh water, groundwater. And I think we got very good evidences from the numerical modeling that we found quite good indications for such a paleo channel at this site. Future trends in exploration. We are now going to design a system for a client in Southeast Asia to develop a fixed wing aircraft that can carry an EM system. This system weighs 5 kilograms and will be attached below the fixed wing UAV and for takeoff and landing. But when it's airborne during production, it's suspended below the fixed wing UAV and towed behind this UAV. It comprises 3-axis induction coils and an IMU that also actively controls the direction of the bird and also measures the attitude of the induction coils. This aircraft can carry 5 kilograms, has a wingspan of 3.6 meters. Takeoff weight is between 25 and 30 kilograms. The flight speed is between 80 and 145 kilometers per hour, and it can stay airborne for at least 3 hours. We don't use a telemetry on ground anymore. We will use Iridium satellites to get control over the aircraft over long-range telemetry. Another possibility in the future will be to use not only one electric source, but multi-source positions and a swarm of drones. This is an example that was provided by Dr. Brian James, a very good colleague of mine from Seattle, who has developed a methodology which he calls interferogrammetry TEM imaging, using many source positions instead of only 1 or 2. It will help to improve the resolution by far. So this, in order to get higher resolution of a target in the subsurface, this methodology is supposed to be superior over other methodologies. But to be efficient, it requires multi-sources and a swarm of drones. It cannot be achieved by ground measurements. This takes too much time.
Johannes, not to cut you off, but
yeah, this
time
was
to start wrapping it up. Yep.
This was already the last slide. Okay. Thank you very much.
Thank you, Johannes. That was a very eloquent and important keynote. You addressed some of the important key drivers of those classic Richard Shoddy images for or the need to look undercover, those statistical images for the need to look undercover, as you mentioned, copper, nickel, and some of these other critical minerals are kind of taking center stage in the mineral exploration world. And that trend is, further powered by government commitment to go net zero. So thanks for bringing that to the forefront. It was a really nice way to frame your case studies and a great overview. So thank you. We are over time, but if anybody has a burning question, you can put it in the chat. I'll take one question and we'll hopefully get it answered quickly and address the rest during discussion. Let me just take a look here. I'll take one question. We've got lots of questions. I'll take the first one that came through from Jean-Paul. Johannes, a very interesting subject. Which modeling and inversion tool are you using? And did you perform 3D inversion?
Yeah, this is a very good question. There are numerous codes available, but usually there are a lot of others, and this is one big obstacle that avoids using them commercially. I now have access to a 3D modeling code that was developed by a German colleague from Berlin and Oregon State University. They commercialized it. It's a full 3D EM code, which also allows to include topography and a control source, horizontal electric dipoles, and loops.
Okay, thank you. Thanks again, Johannes. And yeah, we have lots of other questions here. We'll take them in discussion if you're able to stick around.
Perfect.
We'll, go on to our next speaker.
Yeah, that's a great talk, Johannes. The next speaker, his title is Parameters for Drift Prospecting Using Remotely Piloted Aircraft Systems in British Columbia's Interior Plateau. His speaker will be Easton Elia from the British Columbia Geological Survey.
So, hi, my name's Easton Elia. Today I'm going to be talking to you about drift prospecting and about some of the field programs we've conducted using remotely piloted aircraft systems, or RPAS, in the Interior Plateau of British Columbia. I'm presenting today on behalf of myself, Travis Furby, Brent Ward, Melvin Best, and Robert Shives. This research is in collaboration with the British Columbia Geological Survey and Simon Fraser University. So the study takes place in British Columbia. This is the westernmost province of Canada, located north of Washington State and south of Alaska and the Yukon. This project was completed over the summer of 2021 and 2022, based on the Kalkalkalak Highland Valley and Alkalik Mount Poly porphyry mining districts. These districts are located in the Interior Plateau, indicated by the darker section in this map. This is a physiographic region hosting many of the province's other porphyry occurrences. Exploration in the Interior Plateau, however, has been traditionally limited due to the thick glacial deposits, leading to very little exposed outcrop in the area. Many geophysical and geochemical techniques have been applied to try to see through or to understand glacial sediment cover before other more costly exploration methods like drilling. So one of the ways geologists have attempted to understand the buried mineralization is through a technique called drift prospecting. As a glacier travels over an area, it erodes the rock surface and deposits subglacial till made up of eroded bedrock down ice of where it originally existed. Sampling tills on the surface allows you to look for mineral and geochemical anomalies produced by these eroded deposits. As you can see in the first figure, the till dispersal creates an exploration target that's larger than the mineralized bedrock body itself. This is an image in plan view and then in section view here. If ice flow is well understood, like it is in this figure towards the left of the page, you can trace these anomalies back through the till to their mineralized bedrock target. The figure on the right shows the typical distribution of samples based on copper concentrations surrounding Mount Poly mine. And the mine isn't displayed on this figure. However, its location can be inferred pretty easily by the characteristic till dispersal pattern, with a sharp head of high concentration values and then reduced values further down ice of the deposit to the northwest. So how can we use remotely piloted aircraft systems to detect dispersal in till?
Well, porphyry systems that commonly produce these viable mineable occurrences in the interior plateau, like Highland Valley and Mount Poly, are part of a porphyry system that have potassic alteration surrounding the ore zone, and that's indicated by this orange color here. In these systems, magnetite and potassium are both increased, and when they're eroded, produce tills enriched in both magnetite and potassium. Magnetometers can be used to detect near-surface magnetic signatures from the till units, and gamma ray spectrometers can collect potassium content in the upper 30 centimeters of the Earth's surface. The figure on the left shows a porphyry system with increased magnetite resulting from potassic alteration, seen right here. And above this, we have a magnetic intensity profile from around the deposit. As you can see, the highest intensity is directly over that zone of potassic alteration. On the right, we see a figure of Mount Poly with potassium percentage values. We can see the highest concentrations are at the deposit here, and they fade in the down ice direction, characteristic of the drift prospecting pattern you saw in the previous slide. So this is the platform we used in the field. One of the goals of this project was to use commercially available remotely piloted aircraft systems and sensors so that the method could be easily adopted into industry. It took a bit of work to get all these systems working in unison, but by the end of our field seasons, we nailed down a workflow and everything ran relatively smoothly. For the actual aircraft, we used a DJI Matrice 600 Pro mounted with a radar altimeter from SPH Engineering. The altimeter works with the Universal Ground Control Station software to maintain a constant flight over changing topography seen in the first figure here. This is essential for flying gamma ray spectrometry surveys because gamma rays from the ground attenuate their signal exponentially as they travel to the sensor. And for both magnetics and radiometrics, the radar altimeter produces more accurate results and eliminates some complicated post-processing height corrections. Since we're flying so close to the ground, regions of clear-cut trees or cut blocks, as seen sort of in the background of this photo, are required to conduct a survey. This restricts the utility of the aircraft by forcing us to fly only in areas with recent logging. However, it's essential to fly as close to the ground as possible to maintain the data resolution and quality for this application. So this is the magnetometer we used in the field. It's the GEM Systems drone mag. The sensor was slung 2.5 meters below the aircraft to account for noise produced by the electric motors. And it was flown at 5, 7.5, or 10 meters above ground, depending on the conditions within a cut block, such as vegetation, height, or density. The sensor was flown at 2 meters per second to reduce swinging and collected data every 20 centimeters on the ground surface. To show you the scale of some of the data we collected, I want to first compare results from a more typical RPAS survey to the results we collected from our ultra low altitude RPAS surveys. So the typical survey seen in the background of the image here was flown over trees at 100 meters above ground level at 10 meters per second with a resolution of 3.33 meters squared. Our low altitude survey located here was within a cut block at 10 meters above ground, 2 meters per second with a resolution of 1.67 meters squared. In the top right corner, you can see the flight lines for the smaller RPAS survey. We did 5-meter line spacing and 25-meter tie line spacing on this. Comparing the two, you see the same overall trend in the data with high values to the southeast and lower values to the northwest. Compared to the traditional survey, the low altitude survey has both higher maximum and lower minimum values. This scale of data was collected to gain more resolution, potentially from the shallow near surface magnetite in an attempt to separate the response from till versus bedrock. And processing these data were mainly performed in Oasis montage software, with the exception of a diurnal correction being performed in GEMLink. In the following results slides, I want to compare the RPAS data we collected to some of the already known and accepted magnetic collection methods. So this image is the same small size survey we looked at in the previous slide, except for this image shows first vertical derivative of the magnetic data, and the points represent magnetic susceptibility measurements collected by a ground susceptibility meter. The penetration depth of the susceptibility meter is relatively shallow. Therefore, it's a better assessment of magnetite and content in till than a total field magnetometer would be. The first vertical derivative in the background here, in theory, will highlight some shallow features by enhancing the short wavelength component of the field and produce something that could be comparable to the magnetic susceptibility data. As you can see, the susceptibility data correlates moderately well with the vertical derivative, except for in this low point here in the middle of a high. And this could have been caused by many factors, including like poor contact with the ground instrument on the surface. Through the time using the RPAS instrument, we've had errors with the sensor becoming out of line with Earth's magnetic field and collecting poor quality data. Some of the terrain following features produce a lot of swinging and cause this out of alignment and result in unlocked data that ultimately has to be deleted from the project. So in this figure, I just wanted to compare some of the RPAS data we collected to the regional magnetics for the area. In the background of this image, we have the regional magnetic survey from Mount Poly collected by a fixed wing aircraft at 120 meters above ground level. Ice flow in this image is to the northwest, indicated by this white arrow. And then on top of this image, we have results from 3 RPAS magnetic surveys collected down ice of the mine located here. The first survey collected data in an outcrop near Mount Poly mine over magnetite breccias adjacent to the ore zone. And then down ice, we collected 2 additional surveys over subglacial tills. As you can see from the image, the total field magnetics correlate with the regional trend and decrease away from the deposit, seen by these maximum and minimum measurements here, here, and here. The pattern doesn't represent till alone, however. Instead, it's more of a bulk response from both bedrock and sediments. And at the moment, we're working on solutions to try to extract the magnetic signature from the top 1 to 5 meters in order to understand if the till has been enriched in magnetite. And so if you guys have any recommendations on how to do this, I'd love to hear from you after the presentation. Onto the radiometric side of things. And since it's more of a fringe method in terms of geophysical techniques, I thought I'd provide a quick summary of how it works before we get into some of the data we collected. Gamma ray spectrometry is an exploration technique. It's been used in Canada for about a half a decade. And overall, it provides quantitative measurements of radioactive elements, potassium, uranium, and thorium. It does this by converting gamma rays from the ground into a light scintillation and an output voltage related to the decaying radio element. The scintillations are counted for each energy window, seen in this top figure here, and then used to calculate those elements' abundance. Different rock types have specific radio element concentrations and this provides the ability to distinguish rock type. The system we used to do this was an RS-530 from Radiation Solutions Incorporated. It has a total weight of 3 kilograms and uses a 3x3 sodium iodide crystal. Flying at 1 meter per second, it collects a data point at every meter. And at each site, we use the exact same survey grids for both magnetic and radiometric instruments. So to process the data, we use RadAssist, RSI's proprietary software to correct for height, noise, and convert counts into radio element concentrations. And then ArcGIS was used for some manual spatial correction, and Oasis Montage was used to grid the data. Here we have the results from the same survey you saw in the first magnetics example, but now with potassium percent collected by the RPAS gamma ray spectrometer. I'm only showing you potassium instead of thorium and uranium because potassium is directly applicable to that potassic alteration phase of a porphyry system. The image on the right shows potassium concentration with individual potassium measurements collected by a handheld gamma ray spectrometer. And you can see that the correlation where high values and low values match in both data sets here and here. And we have an overall trend of high values in the northwest and lower values in the southeast. So onto a more regional look at things. The background of this image is potassium values collected by a fixed wing system at Mount Poly at about 120 meters above ground level. And on this plot, we have 3 RPAS surveys again, and Mount Poly is located right here. we have the one closest to Mount Poly was collected over that bedrock unit, and then 2 over subglacial tills. On top of these grids here, we have single point measurements from that ground instrument, handheld gamma ray spectrometer. And you can see that the regional, the RPAS, and the ground data all conform pretty well. We see the highest values at the outcrop nearest Mount Poly, with the next closest survey having the lowest values, and then the last survey is somewhere in the middle. This does not produce the decrease in potassium emissions from the mine as we'd expect from drift prospecting data. However, it's important to note that Radiometric's instrument can only detect gamma rays from the top 30 centimeters of the Earth's surface. And depending on the soil content and moisture, this response can change. This is illustrated by the organics polygons, represented by dotted outlines, that attenuate gamma rays due to high water content and lack of mineral soils, resulting in low values that you can see here, here, and here. And the same has occurred with our data collected by the RPAS. And even though both survey areas are located on subglacial till, here and here, they have very different sediments in the top 30 centimeters. The survey closest to Mount Poly is exposed bedrock, creating these high values. The next is primarily LFH or organic soil in the top 30 centimeters. And this sediment lacks minerals from the till and holds more moisture in it, therefore producing less gamma emissions. And the last survey is primarily B horizon mineral soil in the top 30 centimeters. This is a modified till unit that's more representative of the subglacial till below, leading to those higher values. So overall, I can say that the project did tentatively work. We achieved our goals in seeing that commercially available hardware and software can be integrated to fly these low altitude active terrain following missions. We know that the RPAS magnetic data and radiometric data are high quality and can fill a scale gap between traditional airborne and ground-based surveys. We have found that the magnetic and radiometric data correlate pretty well with their ground equivalents that we collected with handheld instruments. And the radiometric data does measure response from till, as long as that till is in the top 30 centimeters of the sediment profile. So to collect meaningful data from for drift prospecting, the survey size, I believe, has to be increased drastically. It's very difficult to do this in South or Central BC due to the amount of the size and the scale of the forests there. But it may be possible in high latitudes like the Arctic or high altitudes like the Alpine, where vegetation cover is reduced. Our next step is to try to really isolate that magnetic response from the upper 0 to 5 meters of sediments in order to assess the application of that magnetic data. So I'd like to thank the following companies for their support over the history of this project. There's been a lot of moving components, and without them, this wouldn't be possible. So thank you.
Thank you. Easton, we welcome any questions. Thank you for that excellent talk. Was there any attempt, Easton, in redoing the measurement where you had the mag sus being anti-correlated with the 1VD, or any conclusions as to why we have that anti-correlations?
So the mag sus meter was one with a big pad on it, and we found at times where we would put the pad on the ground, we'd get like poor contact, and it would take a few tries to get a reading out of it. And that all depended on like how much debris was on the surface, and if we can get good contact with the ground. But mostly we would run sort of our mag surveys one day, ground measurement the next, and then sort of move on from that area, maybe processing stuff later that night or something like that. And so we were kind of already like moving on by then. So no, we didn't attempt to redo it, and we kind of looked at the data a little bit too late, which one of the great bonuses of doing stuff with RPAS as opposed to fixed wing is that you can process things in the field and get results in pretty much near real time. And I think with a little bit more practice and a little bit more of fleshing out of some of the details on the day-to-day, we can start to do that, where we can go back and take additional measurements, that sort of thing.
Yeah, some good lessons learned then. Thank you, Easton.
Following speaker, it's Bruno Gavazzi. His title is Near Surface Fracture Field to Deep Basement Features Assessment in the Rhine Graben from a 50-meter above ground level magnetic survey using a compact drone solution. So Bruno, the floor is yours.
So let's go. So hello, everybody. First, I wanted to precise that the result I will be showing now are the results of work I started at university before moving to a small company called NRX. I've been recruited at the University of Strasbourg in 2015 after my PhD to take the lead and develop a little group on applied magnetic methods. I've been working there for 6 years, and then I moved 1.5 years ago to NRX to take the head of the geophysical department. And so the study is focused on the Rhine Graben to simplify the area. It's a rift system between France and Germany. It's roughly 50 kilometers wide and 300 kilometers long. And it's resulting from the Alpine orogeny that created an uplift of old Hercynian rocks and an extension that created the basin so the Hercynian rock are outcropping in two massive east and west, and you've got a basin with a sediment cover which is up to 2 kilometers in thickness. And this on the right is a map of the basement lithologies and the main structural features, which are thought to be mostly north 30 degrees here. Why is it important? Because of geothermal projects. So here we are in Strasbourg. It's where my office here is. So here we are more or less in my backyard. And you've got some academic wells and industrial demonstrator for high energy geothermal project. And so the area has been mapped with magnetic gravimetry data and some seismic lines to make some industrial project in the Strasbourg area for electricity and heat production. So also some lithium project, because the fluids within the wells have a high concentration of lithium. So there are some projects starting about that. So there are two wells that were built, one in the north of Strasbourg, one in the south of Strasbourg, from two concurrent companies. And unfortunately, after the targets are 4 kilometers deep within the basement rock, and unfortunately, after when the fluid were put into pressure, it created some induced seismic activity in the east, and now for 1 year all is stopped. And we need to understand better what is happening in the area. And so I will go quickly over that. That's what I really, we are a bit late, so let's be quick. It was just to show on which, that's the interpretative map on which the geothermal project were built, with the main faults on north 30 degrees. So the problem is that there are some inconsistencies. If we look at some surveys in the massif in the east, we see that where the basement rock is outcropping, the main structural features are more east-west. So roughly between north 70 and north 90 degrees. So the question is, are they continuing into the basement? Are they more important than what we thought first? And another problem is that the seismic interpretation is done on 2D seismic line with 3 to 4 kilometers apart, and the geometry is quite complex. It's really 3D, so the interpretation is quite hard to do. And another problem is to do 3D seismic in the area is more or less impossible. There were two projects, but it was stopped by the local people do not want to have some big seismic trucks and geophone everywhere in the area. So that's not a possibility. I wanted then to remind you, I don't know how familiar you are with magnetic methods. It's a passive method, so we are measuring the magnetic field above ground level, and we measure the spatial variation of it, and we are looking at small anomalies that are created by contract of magnetization between different materials. So with a very simple object, we will have this kind of shape with a plus and a minus. We cannot talk directly about depth because it will depend. We have a superimposition of different contact within depth, and the deeper it is, the blurrier we see it. And when we have complex geometry, we have maps like that. And so then we need to use processing tools to extract position parameters of the different sources. I wanted to talk quickly also about the detection thresholds. And why do we want to do drones? Because we can get close to the ground. And why is it important? I put here an equation of a very simple source of the magnetic field of a very simple source, a spherical source. And just for this equation, keep in mind that what is varying is m, which is a contrast of magnetization. So you see that it will move linearly with increasing the contrast of magnetization, and r is the distance to the source. And you will see that it's decreasing quite quickly with the distance. So the distance is the most important parameter. So if we want to get more detail, high resolution, we need to get closer to the ground. When we are on the ground, we have difficulties. It can be very slow because of obstacles. So it's why drones are interesting. Yeah, usually drones are, magnetic measurement drones are done with absolute magnetometer, scalar magnetometer. Here you have a commercial picture from Geometrics. It's not all, but most of the presentation we saw before. It's a very common thing. So it's roughly around 1 kilogram. The different systems are absolute device, really precise, and you cannot really compensate for the effect of the drone. You could, but here I want to do high resolution, so I want to hunt the nanotesla. So I need to correct really precisely the effect of the drones. So usually you deport it from the drone to not have effect. And now we enter into the basis of my research, which are the application of flux gate to do magnetic measurements. Why? Because flux gates are pretty cheap. This one for Bartington is cost around $3,000. You can get some at $2,000. It's pretty lightweight. This one is 80 grams. But there are relative devices that are prone to errors that you need to correct, but they allow also the compensation, mathematical compensation of the effect of the drones. So about the compensation, I base most of what I will show after on a paper from Munshi in 2007. In this paper, they showed that if you take a sensor with a device, a measuring device, and you make a rotation around a fixed point, you will record variations, which are errors due to the errors of the sensor and of the magnetization of your device, the carrier. And so through a quite simple inverse problem, you can compute correcting factors that you can apply. And here in dotted line are the results. So you have the variation when you do this movement, this change of attitudes. And after correction, you have your bold line here. And they showed that was for ground measurement, and it was enough precision, a few nanotesla for application for detection of unexploded ordnance. And now it's used every day by a French company, which is a part of the big construction group Vinci, to depollute field from First and Second World War. So now let's go to my research. In 2015, 2016, I started to play with compensation and on different carriers. Sorry, in an area, I tried it on a small ultralight aircraft, so it's less than 500 kilogram aircraft. The sensor are in the wings, at the end of the wings, and you can see the results at 100 meters above ground in an area not so far from Strasbourg. And keep in mind that here we have only 4 nanotesla, so it's why you have some noises. There's at some building, it's an old airbase here, and we get a pipeline here with an anomaly of about 2 nanotesla. So we're very happy, and we moved to drones. So we went to the same area, got over the pipe at 5 meters above the ground, and we could see it. We were quite happy. It's 150 nanotesla. Here's the magnetometer is on the foot. This drone is a military-grade drone. We could use it because we work with the French Center for Atomic Energy that has a department for military applications. So we could use this drone. It's quite heavy. I don't remember, 20 to 30 kilograms. It's with thermal engine, and so the resolution, the precision was not super good because we had some effect of the rotors, but it was a few nanotesla, around 5, and it was enough to map a pipe, which the effect at 5 meters was 150. So then I wanted to move to smaller drones. Why? Because it's more compact, it's more practical, it costs less. So here it's some tests we did on a DJI Matrix 100. So we attach a drone. So it's a bit apart. You see that it's a bit apart, around 60 centimeters apart from the body of the drone, because when I say we do composition, it's of all the static effects, and of course rotation of the engines are doing noise, and also it's varying through time. It's quite complicating to correct, so we want to be debated a bit to not have a significant effect. So with that, we could flew in the Caribbean on a geothermal project with the French Agency for the Development of New Energies. So we flew at 100 meters. Here you have on the left with some interpretations. That's basically some structural, we are not sure, some of the part here are some flows, magmatic flows, and some are faults, and here's some surveys at 25 meters. I just wanted to highlight that the closer you go to get to the ground, the more resolution you have on your objects. So, and now we are back in the area. If you remember the seismic lines, we did some survey, we did some development on the very small drones. We work with a company called DFE, who do the digitizers. That was the first prototype. We put that on a Mavic 100. The whole system weighs, the drone is between 800 and 900 grams, I think, and the whole system is 1.2. The advantage you have small drone like that is that you can put it in your luggage in a plane. You can take it in a train. You can get in the plane with how many battery as you want. And it allows to cover, the statistics where we cover this area. We covered it in multiple days. We flew in this part in 2020, and this was in 2021. So it was a bit like our playground to make some development. And we managed to do 70 square kilometers in this area. Here you have all the lines. It's at 50 meters above the ground and with a spacing of 50 meters. And here are the results. So you've got on the left a magnetic map of the magnetic anomaly, where you can start to see electric lines here. That's two electric lines. And you see very well the outcropping basement rock here in the massif. So here you have a range of 700 nanotesla. That's quite large. And when we go, we reduce the scale, we start to see some very large wavelengths anomalies that are starting to appear. So on that, I did some reduction to the pole. I changed the scale here to an equipopulated scale to see all anomalies, and you can see some main direction appearing here. I just pointed up. I did also some upward continuation, 250 meters, to help to see better this large wavelength and to reduce the high wavelengths. But this, we interpreted it as a limit, not a structural one, and we'll talk about it later. But we see some orientations that are quite interesting and quite consistent with what we see in the outcrops, and not exactly what we see, what we thought before. So here are on the left, it's an extract of the map I showed earlier with the main structural features that were not known but expected, interpreted. And here on the right, it's work in progress. So it's really careful interpretation of the main contact we see right now. So you can see that one is fitting well, but the other are a bit different to what we thought before. So we're very happy about that. And then we started to look at what we could extract more from this high resolution survey. So I played a bit with derivatives. So that's first order, second order. You can see the little problem in the surveys. Here it's a zoom of this spot, and you can see here it was not flown exactly the same 8, and I tried to correct it, but not thoroughly enough. So you see the little bit of error. But what was really interesting is this pot. So the pot, it was like a big potato-shaped thing before, and you can start to see a lot of lineaments, and that's really interesting because it's correspond to a fracture network. We know here a bit on closer to the massif. And so if we plot it, that's what was known from outcrops or expected from outcrops and morphology. And here we completed it within parts where it's covered by tertiary sediment covered. So we were quite happy with that. We showed that with a 50 meter survey. You can map both very subtle near surface things and as well deep contrast within the basement. And what I wanted to show to you is that with this compact solution, you have a very cost-effective and highly adaptable solution. You can take it on the plane, as I told it before, and it costs not very much. The drone is like a few $1,000s, and the system is not commercially available for the digitizer, but it will be very soon. 30 units have been sold to partners. It will cost a few thousand too, and the sensor are also a few thousand dollars. So with less than $10,000, you can get a fully functional system. And that's it for me. Thanks.
Thank you, Bruno.
Thank you, Bruno. Sorry, Juan. I have one question. I'll take one question here from Alistair. And Alistair asks, how did the fault interpretation compare to the results from the seismic survey?
That's work in progress, because for the moment we just had images of the seismic lines. We signed some agreement to get the data, but we did not get it then yet. And the main thing I plotted, they correlate with some limits we see on the images, but we are not sure of the position because we got just images with GPS data of position. But it correlates well. But in more detail, more subtle limits, we are not sure. So we want to get some look at the data first.
Yeah, it's a nice compact system. As you mentioned, you can take it on the plane with you. And Ed Cunyon mentions that impressive small mag system. So that's his comment there. So thank you, Bruno, for that really interesting talk and presenting that impressive little system.
Yes, next speaker, its title is Suppression of Surficial of Maghaemite Magnetic Noise Using an Unmanned Aerial Vehicle Deployed Magnetometer. And Adam Kroll will be our speaker with Air Geox. So Adam.
Okay, thank you very much for having me today. So yeah, the talk is on suppression of surficial maghaemite magnetic noise using a drone UAV. So this talk was predominantly written by Nick Doreen, and Nick Doreen is the principal consultant for MITRE Geophysics, and he also has an affiliation with the University of Tasmania. And my name is Adam Kroll. I'm with a company called AirGeoX, and we do drone geophysics. So the case study is of an area called Tennant Creek, which is smack bang in the middle of the country. It's quite a remote area, and it's an area that has had mining since the early 1900s up until 2005. And it was a very rich mineral area, actually. So in the 60s, it was the most profitable, highest gold grade area in Australia. And over its time so far, it's produced 5.5 million ounces of gold and 470,000 tons of copper. Yeah, so at the moment, a private, so there's no mining in the area now, but a private company has come in and wants to restart mining. So that's the push for the exploration happening now. So this is a shot of our office, and you can see it's a pretty nice spot to have your office. There's a lot of really large plains with these mesas here, sort of dotted all around the shop. We're sitting on top of a mesa there. So with the drone, we fly a multi-rotor. We fly it between 40 and 50 kilometers an hour when it's on the flat, and then we slow it down when it needs to climb and come up the edge of these mesas, because the mesas are very steep. So the target at Tennant Creek is what's called an ironstone gold copper, or IOCG deposit. And the ironstones are made up of hematite and magnetite, making them extremely, magnetic. So if you're exploring in that area, you're looking for IOCGs, really the best bang for your buck is magnetics. It's cheap to acquire, and it directly identifies your target, which doesn't always host gold, but quite often does. So essentially you're looking for, I should say that the ironstone that you're looking for can vary in size between a few hundred meters width and down to 20 meters width, and typically they're thin lenses, so they're quite shallow in thickness. And the client has said to us, well, we want to find anything that's down to the size of a car. If it's near surface, we'll mine it. If it's down to the size of a car. So what we needed to do was find a solution that was extremely high resolution. But one of the main challenges to this area is that we have this surficial feature called maghaemite. So a lot of Australia is covered with a regolith layer, and the regolith obviously oxidizes the minerals near surface and transports them, breaks them up, breaks them down. So maghaemite is produced by the oxidation of magnetite, and the oxidation process gives rise to superparamagnetism as well as remnants. So what happens is you've got this, you've got these small bodies that are extremely magnetic, and that's essentially the same as the target that we're trying to find. So the maghaemite has a similar wavelength and a similar amplitude to the target that we're looking for, which is a problem, obviously. So in magnetics, essentially a common rule is that the wavelength of the geology you're trying to measure, or that you can measure, is a 1-to-1 ratio with the distance between the magnetometer and the geology. So if you've got a geological unit that comes up to the surface and you're at 40 meters altitude, you'll be able to detect geological units of 40 meters wide or more. And if you are at 20 meters, you'll be able to detect geological units that are 20 meters wide or more. So obviously a manned plane is probably out of the question, because with those mesas around, it can't really get below 40 meters. Helicopter the same, so helicopter could go a little bit lower, but it's not going to get down to that 10 meters that you want to detect an ironstone the size of a car. So then your last two options that you're left with really are walking or drone magnetics. And obviously walking, you're only 2 meters above the ground, so you're going to detect wavelengths that are 2 meters wide or wider. And drone magnetics, if we're flying 10 to 15 meters, it'll be 10 to 15 meters wavelengths that we can detect. So a little bit about our drone magnetic system before we show you the data. So we have developed the magnetometer bird in-house, and it has a very sensitive cesium vapor magnetometer, 1 picotesla per square root hertz sensitivity. We also have 20 hertz GPS. We have a very accurate 10 degree of freedom IMU, laser altimeter. We've got the data acquisition system in there. All the data gets stored to an SD card. It includes the battery, and the whole lot weighs 500 grams. And we tow that under the drone that's pictured in the bottom right there. That's a photo of it being towed, and it gets towed 20 meters under the drone. And essentially it's a brilliant system for Australia and other areas. Well, it's a brilliant system in total, really. I mean, it's we can fly at any speed. It's not sort of limited to a certain speed. And the best thing about it really is that we compensate the magnetic data. So we go up to altitude, we fly a figure of merit, and the heading error of the magnetometer is about 1 nanotesla. And post compensation, we bring that heading error down to 0.1 of a nanotesla. So it's very light, can acquire data very fast, and has very low noise and very high sensitivity. So Mauritania is a deposit that was discovered in 2015. That's when it was first drilled. Drilling so far has generated 29,000 ounces of gold at 3.5 grams per ton. And as I was talking about before, that with that private mining company, they will essentially dig this and extract gold. So the history of the area is that there was a fixed wing manned aircraft that flew in 1998, and it flew at 60 meters above the ground, and it flew a huge area. And when you look at the huge area, this anomaly looks really tiny, but when you zoom in like this, it looks like a booming anomaly. The anomaly there for the fixed wing is a 16 nanotesla anomaly, so it definitely should have been picked up sooner, but anyway, it was drilled in the year 2015. So after they put in the first drill hole, they thought, oh, we'll follow up and we'll find other deposits around there. So we'll do a ground magnetic survey. And the ground magnetic survey had a line spacing of 10 meters, 2 meter sensor height, and they used a Syntrex CS3. And what we notice with the 2 meter flight height is we can see all of this speckled material around here, down here, and sort of continues down here. It continues over the whole area, really. And in the profile, we can see these high amplitude, high frequency features. So those features there are the maghaemite, which is noise on the surface. And if you're looking at the profile, you might go past that ironstone anomaly, but looking at the grid though, it's obvious it's there. But that's quite a large anomaly. It's a few hundred meters wide, and if you had a small little 10-meter wide anomaly, you certainly wouldn't pick it up in amongst this maghaemite. So the drone magnetics was flown again at a 10-meter line spacing, and that was to provide a one-on-one example against the ground magnetics, and we flew it at 15 meters height. So essentially what you can see with the drone mag is that we do have a very good outline of the ironstone in the anomaly. You can see a very good signal to noise ratio between the anomaly and the background noise. And we're identifying a lot of these smaller geological features. There's a trend going through there that you just can't see in the ground mag. So another area that we flew is called 330, and that's right next to a mining district that had very high grades, sort of 50 to 60 grams per ton. And they had a fixed wing survey flown. That should actually be 40 meters altitude. So the mag survey was a lot lower this time. And yet you can see it's all very smooth, all very, just very smooth. It looks like there's been a lot of filtering done after the flight, because you're definitely not seeing wavelengths of 40 meters in there. So it's very doubtful you're going to detect an ironstone that's only 40 meters wide. We go to the ground mag, and we see the ground mag here has, again, this speckled magnetite effect all throughout the data. So again, are some of these units due to ironstones, or are they due to magnetite? Not quite sure. But we can see quite a high resolution. I mean, I think a lot of these features through here are geology, but again, it's obscured by the magnetite. So the drone mag, again, shows good resolution, but just that 10 meter or that 15 meter height above the ground has suppressed that maghaemite high frequency response. So all in all, the drone magnetics worked. It got the client what they wanted, essentially. So if you were a client and you were looking at doing a fixed wing, if you're looking at doing a magnetic survey in Australia, the drone technology is extremely favorable. So these are common figures for Australia. So if you want to cover large areas with a fixed wing manned survey and you don't need higher resolution, yeah, you'd go with a fixed wing manned survey because the cost is lower than a drone. But for a helicopter manned survey or a walking survey, there's not much point in doing that over a drone survey, because the drone survey is cheaper. It gives you a better resolution than the helicopter survey. And so there's no real need to ever use a helicopter manned survey. But the only time when you would do a walking survey is if you were confident that there was no surficial noise. So there was no maghaemite, there was no transported weathered material that's going to affect the survey. Otherwise, you may as well just fly a drone survey. So when a client decides as to whether to use the manned plane, helicopter, drone, or ground survey, they need to consider the wavelength of the geological target. And they also need to consider, which isn't often considered, the wavelength of the surficial noise. So noise like maghaemite. They need to consider the magnetic contrast of the geological target versus the background and versus the surficial noise. They need to think about the resolution acquired after filtering to remove the surficial noise. So if you're walking a ground mag survey and you need to do an upward continued 15-meter filter, you may as well just use drone. And then the final consideration is cost. If you do want to cover a large area and you're not interested in really high resolution, you can still go to the manned traditional method. So I just wanted to say thank you very much to Nick Doreen, who wrote the paper, and he also did the petrophysical work on the maghaemite, and he also did thin sections on the maghaemite to determine its mineralogy. And also want to thank Rob Bills, CEO of Emerson Resources. Emerson Resources have been very supportive of AirGeoX. We've been flying there for 2 years now, and hopefully finding them lots of targets. Thank you very much.
Thank you, Adam. I found it really informative that you highlighted the need to consider not just the geometry of the target, but also the wavelength of the noise, the surficial noise, especially in cases you're looking deep undercover, and there is that consideration of surficial noise. Can you speak to the cost there again for the same survey, the cost and the acquisition rate? I think you had a nice informative slide in there.
Yeah, sure. So I'll just bring it up again. Yeah, so here it is here. So the cost, so a manned survey is cheaper than a drone survey. And that's really because they just produce a lot of kilometers each day. With our drone surveys, we have now fixed wing VTOL aircraft, and we're covering much more kilometers per day. So our cost over time will come down. And I believe with some improvements that we're making over the next year, I think we will start acquiring data at a similar rate to fixed wing manned aircraft. And so our costs will come down to being similar to that, but it's not there yet, but it will be in the next year or two.
Yeah, that would definitely help bridge that gap, right? All right, any other questions? Well, I hope you will stick around for the discussion afterwards, Adam. I'm sure there'll be questions there. But thank you again for highlighting that interesting case study from the other side of the world. That was nice to see. Thanks, Adam.
Great, Adam. Our final keynote speaker of the day is Sami Khanal. Title is the Multiscale Crop Health Monitoring using deep learning in remote sensing data. So Sami.
Let me start by providing a quick overview of my research program. The main mission of my research program is to improve the sustainability of agricultural production system by optimizing crop production while addressing environmental quality. Everything we do is focused on evaluating the role of agricultural practices on crop and soil health that in turn influence agricultural productivity and environmental quality, including water quality and soil health. To meet this mission, we focus on various aspects of digital agriculture, including remote sensing, data analytics, and ecosystem modeling. I will touch on some of the case studies relating to remote sensing and data analytics that we have closely looked into or are currently looking into. My research group focuses on the application of both satellite and drone-based remote sensing technology for understanding agricultural production system and their impact. Like I said earlier, for instance, we have looked into the use of satellite collected images, mainly Landsat and Landsat Sentinel-2 for predicting corn and soybean yield, and Sentinel-3 for monitoring harmful algal bloom in the Western Lake Erie Basin here in Ohio, USA. As you can see in the table here, these images, these satellite images come with different resolution and spectral and spatial resolution, and thus are mostly suitable for large-scale monitoring. These images, however, become less useful when it comes to precision agriculture or digital agriculture, which rely on very detailed site-specific data. As such, drone or small unmanned aerial system based remote sensing becomes very useful. Let me first give you a quick perspective on some motivation behind the use of drone technology for crop yield monitoring. Crop yield monitoring system is one of the biggest innovation in the agriculture sector in the early 1990s that enabled farmers to keep track of how their field is performing in terms of yield. And in other words, precision agriculture relies heavily on yield data collected by the yield monitoring system, and, which is typically mounted on combine at the time of harvest. Well, this is the kind of yield data that get collected and using yield monitoring system. Although, as you can see, these images or this map looks like high resolution yield map, but these data are not very helpful when it comes to assessing the yield differences or crop vigor at a crop row level. Let me illustrate what I mean by this. The map here on the right side shows the yield data collected by 8-row harvester. It means corn yield from 8 row. This is the image. These are the points overlaid on the drone images collected early in the growing season. And so the corn yield from these combines, right, 8-row combines, are summarized at a point when the combine stops and harvest the crop at a given time. Yes, now you can have a one row combine mounted with a yield monitoring system to address this data issue, the resolution issue with the data, but it comes at the expense of time to finish the harvesting of the field. So predicting yield map can allow or the yield map at higher resolution can allow us to answer questions such as how big farm machinery impact crop yield, what information can we see in the visual image that we can see. Okay, here is let me try to give you a scenario when a farmer would like to understand yield data at an individual crop row level. This figure on the left shows the kind of machinery that a farmer in the Midwest have access to. These machinery are really sophisticated in a sense that they allow farmer to perform agricultural operation at a very high efficiency, meaning like in a short time. But this machinery are really bulky in size, as you can probably see here. And they come also with a big weight in such a way that the frequent use of this machinery can result in soil compaction, mainly on the section of the field that get contacted by tractor or planter or any other machinery tires. Oftentimes, agronomics call these section called pinch rows. For instance, this is the 16-row harvest, this 16-row planter, and crop rows from 6 through 11 are impacted by either tractor or planter, and other rows are not. So hopefully the map that you can see on the right here highlight how high resolution data could be leveraged to quantify the yield effect of machinery use. For instance, this is the data that gets collected using yield monitoring system, and this is the visual imagery collected on July 6th, and you can see in this map, the kind of like lines going from south to north, right? These are the compactions introduced by the use of big machinery. When we look at the yield data from the yield monitoring system, we don't see those trends, right? So if some farmers are willing to address the soil compaction issues, this data won't going to be sufficient. So we basically look into the issue of how can we leverage the remote sensing data, particularly drone images collected in season to generate high resolution crop yield maps like you can see here. So I'm not going to talk in details about how we created this map, but if you are interested, we do have a publication coming out of this work that you can look into for perspective. Okay, and so in addition to crop yield prediction, other agricultural research area where we have tried to leverage drone images, include mapping of soil organic carbon. And when I say soil organic carbon, we are talking, I'm trying to be very carefully here. So we are talking about mapping of soil property at the top surface, mainly at the maximum 5 centimeter that gets exposed, right? Or can be monitored via aerially. And we are also looking into the use of various sensor mounted on a drone to quantify in-season nitrogen stress, to monitor nitrogen stress, as well as quantifying soybean defoliation due to insects. So again, I'm not discussing this work at a great extent as they have been published in peer-reviewed articles. One thing I would like to highlight here is that though we had been using multispectral sensor, mainly MicaSense radar sensor that comes with red, green, blue, radars, and near-infrared channels for understanding crop yield, soil property, as well as different crop stresses, as these crop or soil property are typically sensitive in the near infrared spectrum. For soil for defoliation, we used high resolution drone images collected at very low altitude. That means we collected it at 10-meter altitude, 10 meter above the ground. Another research, another ongoing work now leveraging drone-based remote sensing includes mapping of maize or corn virus that is very tricky to detect. As we can see, and in the image top right, maize virus create very light lines on a corn leaves. If this virus gets untreated on time, this virus can result in significant ill impact on farmers. So in collaboration with researchers from USDA ARS, we are experimenting the efficacy of various sensors ranging from thermal, multispectral, and from this year we have started looking into the hyperspectral and LiDAR sensor and to assess whether the images or the data collected by these sensors can be used to detect the maize virus and how they can impact on corn yield. So we basically conducted a pilot scale experiment, as you can see here, and the plots showing in red boundary, they are the ones that were inoculated with virus, and then the plots in blue boundary, they were the plots with no virus. So we collected images using DJI Matrice 200 mounted with MicaSense multispectral camera along with thermal sensor. And as you can see here, these are the maps these are the maps collected on July 2014, and then from thermal sensor, and then this is the map collected on the same day using multispectral. We have had mixed success, and that's the reason we kind of have looked into the role of hyperspectral and LiDAR sensor to see if these sensors can detect the virus presence in these treatment plots. We also collected handheld spectroradiometer data that provide spectral signature of a crop at a very high spectral resolution, and we did see some signature created by the virus, but not so much. So we are still in the process of analyzing the data. So hopefully after this year's data, we would be able to kind of pinpoint the sensor that might be useful to detect some of these corn virus. Similarly, in collaboration with plant pathologist here at OSU, we are trying to evaluate if drone images can pick up crop health stress due to soybean cyst nematodes. Soybean cyst nematode is a plant parasitic worm. It is the most ill-limiting disease, soybean disease in the US, and can result up to 40% decline in soybean yields. So treatment of this disease is pretty tricky, mainly because their identification is difficult, as most of the symptoms starts developing from the root of the crop itself. These disease once they get severe, then we can see the crops yellowing, or we can see stunting crop roots, and they can occur in the patches, in the form of patches across the field. So our motivation is kind of to test if we can somehow detect these above ground symptoms that gets reflected via changes in soybean vigor, mainly the coloring of soybean leaves. And so the map here on the left kind of shows the ground truth soybean cyst nematodes population. And you can see there are sections of the field where the crop, where the disease, or where these soybean cyst nematodes are pretty prevalent. This area, and we kind of we collected this image. We collected the images the past summer using multispectral imagery and here you can see how the images of the field look like in near infrared red sensor, right? And then we basically derive one of the most commonly used vegetation indices, which is mainly the combination of red A's and the red channel, right? And we can clearly see that these images are picking up some of the are to some extent able to detect the presence of soybean cyst nematodes in the field. We are again analyzing the data to develop machine learning models to analyze this problem at a great extent. So another project involves the use of drone images to detect a tie line present in the field. And the idea here is to automatically extract the tie line structure. As you can see, this is the visual image collected on April 27th of April in last year, and then you can also see other images in different spectral channels, red A's, NIR, and this is the thermal images of the same field, and the data were collected around the same time. We could see some promises in those images, but again, there are several activities that take place within the field, like the structure that we saw earlier in the map, right? Introduced by the use of farm machinery. So the idea is, how can we separate out this potential tie line structure from the pattern that we saw in the earlier slide that was introduced by machinery. So again, this we are in the process of collecting ground truth data from the farmer operating in this field, and trying to automate the process of detecting the tie lines. And again, the idea here is, how can we quantify the crop yield or the difference in biomass with the presence of different agricultural structure or the agricultural practices. And so there are a suite of sensors or drone platforms that we are currently working with. And as I mentioned earlier, we recently acquired LiDAR and hyperspectral sensor, and so we collected the data for using this sensor this past summer, and we are in the process of analyzing this data in a great extent to pinpoint or to evaluate how do the data coming from this sensor compare with the other sensor. So now I would like to switch gear a bit and discuss a project that we did in collaboration with computer scientists. This project was focused on how can we optimize drone flight planning for data collection for precision agriculture. Currently, researchers as well as industries providing drone data collection services are collecting drone data using a typical lawnmower flight planning design, just like the one that we see. These are the typical, this is the typical flight plan of the drone, and especially in agriculture. I'm not sure how this thing works in other area. So we typically maintain 60 to 70% lateral or vertical overlap between images, so that the images from this agricultural field can be stitched without any issue. The criteria for this high overlap between these images is high, mainly because crops are they look kind of homogeneous within the field, so, and the fields are really large. So to avoid that issue, and especially when it comes to thermal sensor, right? So this overlapping criteria increases up to 90%. So to cover a larger field, this result in an excessive use of drone batteries, right? So we collaborated with the computer scientists to answer questions like, how can we reduce this exhaustive UAS scouting of a field using deep learning? And the idea is mainly to kind of visit only the certain section of the field, like you can see here, only a certain section of a field, and use deep learning technique to basically extrapolate the crop signature or the soil signature in the neighboring area of the of the areas that got collected. And again, this paper has has been published, and if you want to learn more about this, please look at this manuscript. Now, I would like to highlight some of the technical aspects we need to think of when collecting high quality UAS images, mainly for agriculture research. One of the aspects is the use of ground control points in the processing of drone images. This is the experiment that we conducted by placing ground control points in a field, and we use different combination of GCPs, and you can see here the result, the error of the positional accuracy of these images basically is very high if we don't use ground control points, and the error reduces dramatically with the increase in ground control point. This is really critical, especially when we are doing experiment in a small scale, in a small plots like I showed earlier. I would like to skip on this, and then also there's another area that is kind of like critical to consider is the saturation of spectral signature. Most of the spectral signature tend to saturate at a higher biomass, although they work better at low biomass. As we can see here now, even with the increase in biomass, some of the spectral signature kind of like saturate. So these are the problems, especially in agriculture sector, and we kind of like look into how the how different structural component that could be collected by LiDAR, such as plant height, could be incorporated to address this issue. And here is the one of the results that we got that basically shows the difference in performance of a machine learning model for biomass estimation with just spectral signature and with spectral signature and vegetation cover, and this is with the inclusion of vegetation cover and plant and height, and along with the spectral signature. And you can see the performance of the biomass prediction model basically increases with the inclusion of this structural component. So with that, I would like to kind of acknowledge some of the funding sources that provided support to this work. Sorry, I ran out of the time, but if you have any questions, feel free to ask or drop me an email.
Yeah, thank you, Sami, for that interesting talk. And if there are any questions specific to Sami's talk, feel free to put them in. It's a slightly different pivot from our lineup here, but thank you so much, Sami, for presenting for us today. Awesome, thank you. And if not, we can open up the floor for discussion. And I think the discussion, anybody can really chime in with questions and chats, and we have all the panelists. I think we're all here. Maybe we can open up the floor with a large question, maybe a thematic question, and then we can address some of the specific questions that were carried over from each of the talks that we didn't get to. But a thematic question would be, I think, something that any of you can really speak to. How do you guys are in the space, you guys are working with explorers who are using drones. How do you foresee adoption in the exploration space? Where do you see the main trends are going? Are you seeing more and more companies coming to you with the need for drone surveys? Where do you see the trend going in the next 3 to 5 years?
Well, I can jump in on that one. Essentially, that's really the need is what's pushed our focus onto these larger systems. Everyone that approaches us is looking for slightly larger surveys than what's usually possible with more readily available DJI units. Thankfully, since we have that drone engineering background, we can provide those systems. but really it's increasing that footprint. And of course, the constrained integrated mapping solutions.
Yeah, increase for footprint and also perhaps, well, I guess speed ties into that.
Yeah, that really adds something, you know, us here in the consulting industry, getting, you know, what Alex is talking about, a lot of big surveys that are, you know, ranging, you know, acreage more than hundreds of acres, right? That now the drawback is the drone, right? And looking at more feasibilities in the type of drones and for that particular prospect that you're looking for. So I think drone will always be the limitation.
And that's why you see a lot of movement going into electric vertical takeoff and landing fixed wings as well. Of course, they can't fly as low to the ground, but that tech is certainly getting to that point where it can really be adopted in industry.
I think it's also a matter of regulation because MAN aircraft, for example, in Australia or in Africa, you can get pretty low for pretty cheap. In Europe, with ultralight plane, you can get 200-meter minimal when you are not above settlements. Then it's 500. So the range for drone application, when the regulation is more, or to say that it's less hard than with manned aircraft. We have a lot of application that we could do, but to be in opposition with manned aircraft in where they can fly as low as 50 meters in very wide flat areas, I think it won't be possible to get to the same price tag, especially for magnetic geophysics.
How about you, Adam or Johannes? Perhaps any thoughts and shareables on what your clients are seeking from you, or what are the big asks, and how are you kind of thinking of addressing those kinds of blockers? Yeah, I was just asking, what are some of the big asks and blockers that your clients are facing when they're looking at doing a survey, and how are you addressing those blockers of adoption, going with a drone survey versus not?
Of course, there are pros and cons. Ground-based measurements are, in all cases, are the best option in terms of resolution. Yeah, but ground measurements cannot achieve. You cannot do measurements in areas which are not accessible and by foot. And what I see what I saw in the last decade, the mining industry understood that they can achieve they can collect data from areas which were not able to be measured or surveyed in the past. Especially in the last 5 years, I did several projects where it became clear that data collection was only possible by using drones. In some projects, my client compared my results with data acquired on manned aircraft, mainly fixed wing, and it became clear that the resolution from drones was much higher than from manned aircraft. So I think this is one of the main benefits. Areas which couldn't be surveyed due to poor accessibility now become accessible by drones, by using drones, and resolution is much better because drones can fly closer above ground. So this is the main benefit. A blocker can be the costs because due to the very limited endurance of most of the drones, mainly rotary wing or multicopters, the the distance that can be achieved in one leg is very limited. If you can fly only 20 minutes or 25 minutes, you achieve maybe only 6 or 7 kilometers per flight. So you have to do many flights to cover huge areas. So I think there's a physical limit to drones of the size of areas that can be achieved by one drone.
Thank you for that. But they are getting smaller, and we are starting to bridge that gap, as Adam detailed in his call as well, in his talk as well. Okay, we had a lot of questions that we didn't fully get to, so I'll move on to those. I'll start from the top. Our first speaker was Robert. Robert, we had a question that that I think you answered in the chat, but just for our audience here, if you wouldn't mind getting to again, it was from Jeffrey. The question was, the case studies are in glaciated terrains. What about weathered arid terrains like Africa and Australia?
With arid terrains, I just worked in the Arctic realm, where you have a lot of lichen coverage, which is always a problem. But I assume if you are, and what I heard from colleagues, you have those aeolian sediments blasting, I don't know, sand and iron-rich sediments all over the place. And this can be really, of course, noise. You detect things in the hyperspectral, in multispectral, which come from a complete different source. But maybe this can be helpful as well to trace back to deposits, as what we have seen in this talk by this colleague from Canada. So it goes in that direction. And of course, in hyperspectral, multispectral, we work just with the top first micrometer. So anything blocking your ray of light is a big problem for our kind of data. Yeah.
Thank you. And just a reminder, if you have questions from the audience that you want to ask, please place them in the Q&A or raise your hand and I'll unmute you. I had a lot of questions for Filippo as well, but they're more specific. So maybe I'll relay them onto you by email and you can maybe get back to the audience. A few questions for Johannes. Which are the most useful methods to choose when using UAV to run a mineral exploration program, let's say for porphyry copper and epithermal deposits? That was the first question.
Airborne electromagnetics and airborne magnetics are the most used methods, and I would recommend. Radiometrics is also important, but radiometrics on drones are lacking of the payload required to lift bigger volumes of a crystal, of a radiometrics sensor. If the volume should be at least 4 liters, but 4 liters, to my knowledge, they weigh already more than 10 kilograms, and then it becomes very difficult to lift it for a reasonable time, flight time. Bigger helicopters that can easily lift 10 or 15 kilograms usually cost a lot, more than 150,000 euros, 200,000 euros. So it will be not very cost effective. So the problem with the volume of the crystal is, if it's too small, you must fly at a very low altitude above ground, which limits the radius of your measurement. If you fly very high, maybe 100 meters, you must fly extremely at a very, very low speed to collect enough counts per time unit to become sensitive enough. And if you fly too high, you need also a second sensor to measure the counts that come from space. So I think there are a few obstacles to use radiometric measurements on drones. Maybe there is somebody who knows these requirements much better than I do. But in all mining programs, magnetics and EM are the methodology of choice.
Thank you. The second part of that question, I think anyone here can address, seems to be a recurring question. The cost of running a UAV program per line kilometer. I think there was a nice slide in one of the presentations with that, but anyone's welcome to speak to that.
I can jump on that one. I always love this question because the variance is so large. It really depends on your project. It's not like you can just say, this is what it is. It greatly varies. So it's really up to sitting down with the client, figuring out exactly what their needs are, what's the mobilization, demobilization costs on top of just the surveyed line kilometers as well, processing it, all those other things. So it really depends on the needs of the project.
Yeah, it's really interesting talking with clients because they assume that because drones are little toys, that the survey is going to be really cheap. And in fact, it's a lot more expensive than flying a manned survey. So yeah, I find that we really only win work if I can sit down with the client and show them why it costs more and show them that the resolution, the improved resolution that they get is worth paying more for. If they don't sit down for a, predator, like to see the data, they don't ever choose to fly the survey. Yeah, that's what I found.
It is a bit of a bespoke solution where a conversation needs to take place before that decision happens.
If you want to range, for example, what we build the clients for surveys with a small drone I showed, depending on the specification, between $20 and $150 per kilometer. So it's a pretty wide range.
Mm-hmm. There's your answer. It's a spectrum. It's a range. All right, thank you. While I have you there, Bruno, we have a question. Would you be able to elaborate using drone to detect UXO? If you have any resources on that, if you're able to speak to that.
What I showed was more some images of ground-borne measurements. So what is done usually when you are doing mapping is to use with flex gates, is to use a backpack or carried on a quad bike or something like that, 5 to 8 parallel flex gates to make measurement at 1 meter above the ground. And so that can be pretty quick. And if you want you need to have the same specification if you want to fly with a drone. So you have to be able to fly 1 meter above ground. Like a sensor is 1 meter above ground, you have to be precise, like 10 centimeter precision. Better will be better. And I talk a little bit about it in a paper from 2019. If someone send me an email, I can send it. Because we did some tests with Vinci to put it on drone for flex gate on the M600. They are flying right now. They are producing with it, but they are doing it by themselves now. It's a quite big company. They recruited some people from my team, and they're autonomous on that. If you are targeting not huge thing like anti-tank mines, you need to be at 1 meter above ground. So M600 with RTK and not only one sensor, because otherwise a quad bike will be faster than you.
Could I actually ask a question as well?
Of course. Go ahead.
So
I was just going to mention that Bruno's email is in the chat for the user or for the participant who asked that question. So they can maybe reach out to you directly. Go ahead, Alex.
Excellent. Bruno, for that 4-sensor system, that wouldn't happen to be the Census R4, was it? I noticed in your presentation you're using the R3.
No, I do not use a Census one. It's a custom one we did with DFE. It's small box up to 8 channels, but we use only 4 because then you cannot take off. It's becoming too wide. But my only issue with the R3, it's heavy. Yeah, but I did some experiment with it. It's quite good, but I have some noise because the digitizer is a bit close to the sensor in the middle. It's acceptable for XO, but when you want to target like hand grenades or very small objects, it starts to be a bit of an issue. And the sampling is fixed, if I remember correctly. I don't know if with the I made some experiment with the R3, not the R4. So maybe they improve with that.
Excellent. Thanks for the feedback.
Bring things back to you, Filippo. I just saw that a question was asked about your dike, the dike thickness that you chose, the geometry of the dike that you presented in your example. What was that based on? Was it based on the outcrop dike measure dimensions?
No, I don't hear you. Okay, no, it's not a problem. I take this information from the geological information. So I acquired the shape of the dike on the field, and I used this information that for my 2D forward model. So I take this information on the field and I follow the main thickness of the dike along the 450 meters along the quarry wall.
Okay, so it's based on field, publicly available field data. Yeah, if you have anything to add to that question, feel free to jump in or raise your hand in the chat. And also, Filippo, Ed mentioned that he thought it was Ed Cunnion mentioned that it was your example was a good one on how fast magnetometer sampling rates allow for the removal of power line noise without aliasing. So that was just a comment there. All right, I'll bring things around to you, Easton. Hope I'm saying your name properly. A question for you came in asking, did you try any mapping of thorium and potassium, and if it could show potassium enrichment better?
Yeah, for sure. So with the 2021 data we collected, we did some thorium potassium ratios. One thing you have to note about the sensor is, like Johannes mentioned, is it is a very small crystal size. So your counts for both thorium and uranium are pretty small. So it sort of makes a kind of a noisier data set. And then ratios with any radiometric ratio that you do, it's more complicated than just putting potassium over thorium at each data point. There's like minimum statistics for the amount of counts you have to capture for each data point in order to do those ratios. So at the moment, I have the email in the inbox from how they did potassium, thorium, all of the ratios for the regional data they collected with the fixed wing aircraft for my area. And ideally, I'd want to use those same calculations for the UAV data in order to make them super comparable. So I think it'll be a little bit of reprocessing the 2021 data and then the 2022 data so that everything matches up. So yeah, I think we can expect it in the next month or so.
Perfect, that's exciting. Right, I'll roll things over to you, Johannes. We have a few questions that came in for you. One of them is, it appears that the airborne, it's from an anonymous attendee, it appears that the airborne EM system is a frequency domain system. Could you elaborate a bit on how the imaginary component is calculated, and how do you decouple the source signal from the phase delayed secondary field?
Yeah, it's a little bit tricky. The semi-airborne EM methodology uses a horizontal electric dipole on ground with a spacing of at least 1,000 meters, sometimes 5,000 meters, to generate a very strong moment, dipole moment. And the electric current is recorded on ground. At the same time, the EM receiver is flown on the drone on lines perpendicular to the direction of the electric dipole. And the magnetic field is recorded at three components, 2 horizontal, 1 vertical component. It's very, very important to evaluate the phase information, to record the current as well as the magnetic field with extremely high time accuracy. The time accuracy on our system is in the order of 50 nanoseconds. If you don't do that, you lose phase information mainly at the high frequencies. So what we do is we build a ratio between one of the magnetic components and and divided by the current for a given frequency. What's new in our system is that we have many evaluation frequencies due to the very short turn off, turn on time of our transmitter. We create a lot of harmonics. We get 400 frequencies. Usually in traditional airborne electromagnetics, only a few evaluation frequencies are used, maybe 5 or so. And it's both for time and frequency methodologies. We have a frequency. We do our measurements in the frequency domain, and we use 400 evaluation frequencies to estimate a so-called transform function. The transform function, as I said, is created by building the ratio between one of the 3 magnetic fields measured on the drone and the current measured on ground. And this allows us to create a transform function. And the transform function is input in our 3D modeling code. We model and invert the transfer functions. And the transfer functions contain the full information about the conductivity distribution at this measuring point. And usually, if we fly a 1 kilometer long line, we get every 10 meters we get a measuring point, which allows to create a very dense measuring grid and invert this measuring grid and invert the transform functions collected along on this measuring grid. So it's a complex number because what we measure is an amplitude and a phase, or a real and imaginary part. Amplitude and phase can be converted into the real and imaginary part, or other words would be in phase and out of phase part. And it's a complex number which has to be. It contains all information about the conductivity in the ground. Yeah, that's it.
Can I ask a question? Have you tried collecting magnetotelluric data using the same methodology?
Yeah, the magnetotelluric, airborne magnetotellurics is AFMAG. Yeah, so AFMAG has, I think, the shortcoming that you depend on signals generated by the ionosphere. You must get some signals generated elsewhere. You know, you wait for natural signals. You know, and I'm wondering a little bit how it maybe requires stacking, but stacking means time. Yeah, flight time. So the spatial resolution will be very poor if you use AFMAG. In our case, we have a source, artificial source on ground, which generates signals over a wide range of frequencies, from 30 hertz up to 100 kilohertz. So the induction space and induction parameter, which is a function of frequency, is very, very wide. So we can handle near field and far field data very well, because our drone flies within, it takes measurements in the near field, close to the transmitter, and in the far field, which implies to use different methodologies to evaluate the conductivity model. It's very complex because you are traveling between two modes, the near field and the far field, and this requires a lot of computational power to extract the conductivity information from the ground.
Okay, thank you.
Thank you, Johannes. And this question was answered in the Q&A box, but just for our audience here, and anyone is welcome to touch on this. What percentage of EM, what would you say are the percentage of EM surveys occurring currently versus magnetics? And this panel, do you see it gaining ground? Johannes, you had an answer to it, but welcome anybody to speak to it.
I think she meant pentamag. I use not a total field magnetometer. I use flux gate magnetometers with 3 components. And the benefit of using flux gates is they are extremely light. One weighs only 500 or 400 grams, including electronics and data acquisition. So I can afford to carry up to 5 sensors on a 10 kilogram multicopter. The benefit of using 2 or 3 or 5 magnetometers is that you create 5 lines on one flight. 5 measuring lines on one flight, with a spacing of in our configuration, with a sensor spacing of 50 centimeters, half a meter or less. So the benefit is that we can cover, we get more or less a 100% coverage of an area, and also the measuring grid is extremely dense. The line spacing is 50 centimeters, and between lines and along the lines, the measuring point measuring spacing is the order of 10 centimeters or 5 centimeters. And the benefit is that it allows to resolve very small objects we did a test on a military test site where ammunition is buried at known locations at a known depth, and we found out that we can resolve ammunition with a caliber of 3.7 centimeters at a depth at 0.5 meter. This was assured during this test project. So I'm favoring 5 sensors rather than only using 1. I think this is mandatory for any UXO program.
Interesting perspective. Thank you. Any other thoughts, discussion points? I think we got through all of the questions. There were so many. If there are any burning questions, please put them in the chat or the Q&A.
Just a quick
question for you.
Pardon? I'll let you go first, Alex.
All right, I was going to say, what's BHP looking for?
Great question. Yeah, we are now headquartered in Toronto, which is one of our global head offices. So we're fairly focused on copper and nickel at the moment globally. So I enjoyed looking at Johannes's slides highlighting that. It's definitely taking center stage for us.
Are you
looking deeper as is everybody else below cover.
Excellent. Yeah. Are you involved at all with the Explore accelerator that's accepting applications right now?
Explore is a separate program in BHP, which partners with juniors. I sit in the metals exploration group, which has a more global governance for internal exploration. Explore usually partners with other programs.
Sounds great.
Lots of interesting efforts going on. Yeah.
Thanks for your answer.
Yeah. Robert, I think you were going to say something.
I wanted to ask Bruno if the small Mavic Mag is available commercially.
Yeah, more or less. If you ask directly, it should be going public. The plan was before the end of the year. But you can. It's we do not sell. Actually, it's with a company called Geophy. They build the digitizer, and then you buy your system and you fix it on the drone by yourself. But we want to make it a bit more user friendly and to put digitizer within the stick. That will be sometime next year. But if you want the digitizer and buy a flux gate and attach it yourself, you can already do it.
Okay, thank you.
Yeah, 30 units have been sold for the moment, so only to partners. So yeah, please email me. Yeah.
Actually, while we're on that, if all the speakers are able to put their email in the chat, that'd be great. And unless there are any more thoughts, we can maybe round it up. Any of the panelists, you have any thoughts to share? Callum, Laura, I see you're online now.
No, I didn't have any burning questions or thoughts. Just another excellent day at the summit. Lots of fascinating talks, and it's really exciting to see what everyone's been working on since last time. So thank you again to all the speakers. It's been wonderful.
Yeah, it's been a really good day for me personally. I took lots of notes, and I'm excited to see what day 3 holds. So thank you all for your time. I know you're joining in from different parts of the world, and it's dinner time for some of you. So thank you again. And hopefully we will see all of you on day 3, same time, same place.
It will be UXO, GPR, and EM. Same time and same channel. So we'll see you guys then.
See you then. Take care.
Excellent. Thanks, everyone.
Thanks.
Thanks.
Bye.
Thank you.